Welcome, friends. I'm so glad you're here. Whether you're drifting towards sleep, unwinding after a long day, or simply looking for a quiet companion, you found the right place. Before we begin, I'd love to know, where in the world are you listening from? Perhaps you're wrapped in a blanket, sitting by a softly lit window, or resting somewhere under an open sky. Wherever you are, I hope you're warm, comfortable, and ready to wander with me into the silent birth of Earth's eternal companion, the moon that watches from the darkness above. If you find peace or curiosity in these gentle stories, please consider liking the video, subscribing to the channel, or sharing it with someone who might need a moment of stillness too. And to those who've already joined along, thank you. 4.5 billion years ago, in the Hadean Eon, when Earth bears a name that means hellish, the young planet spins beneath a sky that holds no familiar light. No moon hangs suspended in that ancient darkness. No silver crescent marks the passage of months. No tidal pull shapes the rhythm of future oceans. The Earth rotates once every 6 hours. Its day a brief heartbeat in cosmic time. A frantic spinning that will slow only after the events that follow. Above, the solar system remains a construction site of creation. Planetesimals drift through space like cosmic debris. The leftover building blocks of world formation. Gas and dust spiral in vast accretion disks. The sun burns younger and dimmer, casting a weaker light across this realm of forming worlds. In this scattered architecture of the early solar system, a body roughly the size of Mars follows its own elliptical path through the darkness. Scientists have named this wanderer Theia, after the ancient Greek Titaness, who, in mythology, gave birth to Selene the moon goddess. But the collision that approaches holds nothing of myth or intention, only the cold mathematics of orbital mechanics, the inexorable pull of gravity, and the violent poetry of celestial bodies in motion. Theia drifts closer across millions of years. Its trajectory, determined by gravitational influences from Jupiter and the other gas giants, slowly curves inward toward the inner solar system. The approach is not sudden, but gradual. Like the turning of some vast cosmic clock whose hands move across geological ages. As Theia nears, its gravitational influence begins to perturb Earth's early atmosphere, stirring the primitive gases that will later be swept away entirely. The wandering planet itself carries mysteries in its composition. Theia likely formed in the outer regions of the solar system before migrating inward. Its rocky mantle enriched with water ice and organic compounds from the cold reaches beyond Mars. Its iron core, proportionally smaller than Earth's, spins within a mantle of silicate rock that has never known the touch of liquid water or the breath of atmosphere. The surface bears the scars of countless impacts from the late heavy bombardment, a pockmarked testament to the violent youth of the solar system. 25,000 miles per hour. This is the closing velocity as Theia approaches its rendezvous with Earth. The speed seems almost leisurely compared to the hypervelocity impacts that pepper both worlds during this era. Yet it carries enough kinetic energy to reshape two planets. The angle of approach becomes crucial, 45 degrees from vertical, a glancing blow that will determine the fate of both worlds. Had the collision been head-on, perpendicular to Earth's surface, both planets would have been utterly destroyed. Their matter scattered across the solar system in fragments too small to reform. Had the impact been too shallow, too grazing, Theia would have scraped along Earth's surface and ricocheted back into space, perhaps to strike again in another age, or to wander forever in the outer darkness. Instead, the geometry aligns with almost artistic precision. The impact angle is perfect, catastrophic enough to merge the two worlds, gentle enough to allow survival. It is as if the universe has calculated this collision with the patience of a master craftsman, setting up the conditions that will, in 4.5 billion years, allow conscious beings to gaze up at the moon and wonder at its origin. The moment of contact, when it comes, unfolds in geological slow motion. Theia's leading edge touches Earth's surface first, creating a pressure wave that races through both worlds at the speed of sound in rock. The crust buckles and liquefies. Mountains evaporate. Continents cease to exist. The impact point becomes a zone of pure energy where matter transforms into plasma, where the distinction between rock and gas dissolves in temperatures that rival the cores of stars. Theia's iron core, denser and more massive than its rocky envelope, continues downward through the chaos. It plunges deep into Earth's mantle like a molten bullet, eventually merging with our planet's own metallic heart. This is why Earth's core today spins with unusual complexity, why our magnetic field fluctuates and reverses with mysterious irregularity deep beneath our feet. The iron heart of an alien world still stirs the molten currents that generate the invisible shield protecting all life from solar radiation. But while Theia's core descends, its rocky exterior explodes upward and outward in a fountain of superheated vapor. The energy of impact accelerates this debris to velocities that exceed Earth's escape speed. Some fragments travel so fast they break free entirely, scattered into interplanetary space where they will drift for eons as silent testimony to this moment of creation. Other pieces, moving more slowly, arc through the vacuum in parabolic trajectories that will bring them crashing back to Earth's molten surface within hours or days. Between these extremes lies a third population of debris, material moving at precisely the right velocity to remain in orbit around the transformed Earth. These fragments, ranging in size from boulders to entire mountains, trace elliptical paths through space at distances between 10,000 and 50,000 miles above the planetary surface. The orbital ring they form glows with the heat of recent violence, casting an eerie light across Earth's scarred face like a crown of fire suspended in the void. The mystery of isotopic signatures emerges from this chaos. When scientists analyze lunar rocks returned by Apollo missions, they discover that Earth and Moon share identical ratios of oxygen isotopes, a chemical fingerprint that confirms their common birth. Yet the Moon remains mysteriously depleted in iron and other heavy elements, as if only Theia's lighter, more volatile components escaped to form our satellite. The massive iron core that plunged into Earth's depths left behind a moon composed primarily of the outer rocky layers of both worlds, a distillation of stone and metal that preserves the memory of this ancient collision in every crater and highland. The debris ring persists for centuries, perhaps millennia. Individual particles collide with one another in slow, grinding encounters that gradually flatten their orbits into a thin disk. The largest fragments, possessing the strongest gravitational pull, begin to attract and accumulate smaller pieces. What was once chaotic becomes organized. What was violent becomes patient. The process of accretion follows the same gentle laws that govern the formation of planets, but compressed into a timescale brief enough for mountains to witness. Within 1,000 years, an instant in geological time, the Moon condenses from scattered debris into a coherent sphere. It glows cherry red with residual heat from the impact, its surface an ocean of molten rock that mirrors Earth's own magma seas. No atmosphere surrounds this new world. No weather disturbs its perfect silence. The vacuum of space draws away any gases that might escape from the cooling lava, leaving behind a realm where the only sound is the whisper of solar wind against naked stone. The collision that birthed the Moon also fundamentally altered Earth itself. The impact tilted our planet's rotational axis by 23.5 degrees from vertical, the precise angle that gives Earth its seasons. Without this tilt, our world would know no spring or autumn, no migration of weather patterns, no rhythmic advance and retreat of ice ages. The changing seasons that inspire poetry and govern ecology trace their origin to the moment when Theia struck our world with perfectly calculated force. Only took a planetary collision to invent the gentle progression from winter to summer. Only took the destruction of two worlds to birth the silver light that will guide future navigators across unknown seas. Only took the most violent event in Earth's history to create the celestial companion that will come to symbolize romance, mystery, and the quiet contemplation of night. The moon that now drifts peacefully across our sky carries within its ancient stones the memory of fire and chaos. The geological DNA of a collision so precise it seems almost intentional, as if the universe itself paused to ensure that Earth would never lack for a watcher in the darkness above. The newborn moon hangs motionless in Earth's sky, a sphere of liquid fire suspended against the cosmic dark. Its entire surface burns with the afterglow of creation. An unbroken ocean of molten rock that stretches from pole to pole without interruption. No solid ground exists yet on this infant world. No mountains rise from cooling plains. The moon in its first 1,000 years resembles a drop of incandescent metal, perfectly round and impossibly bright, casting red shadows across Earth's own magma seas below. The temperatures at the lunar surface exceed 2,000 degrees Celsius. Silicate minerals, the building blocks of rock, flow like water in this foundry heat. Olivine crystals dissolve and reform in endless cycles. Pyroxene minerals drift through the molten currents like microscopic icebergs in a sea of fire. The entire moon exists in a state that planetary scientists call a magma ocean, a condition so extreme that solid matter cannot maintain its crystalline structure against the relentless thermal energy trapped within. This heat originates not from the sun, which burns dim and distant in the young solar system, but from the kinetic energy of the impact that created the moon itself. Every fragment of debris that fell together to form this world carried momentum from the original collision, and that motion converted to heat upon impact with the growing lunar surface. The process resembles a cosmic forge where gravitational potential energy transforms into thermal energy with perfect efficiency. The moon literally melts itself into existence, each new accretion adding to the furnace that keeps the entire world liquid. As centuries pass, the vacuum of space begins its patient work of cooling. Heat radiates away from the lunar surface at the speed of light, carrying the moon's fiery birth energy into the infinite cold of the void. Unlike Earth, which will develop an atmosphere to trap and circulate warmth, the moon possesses no gaseous envelope to moderate its temperature. Any volatiles that might escape from the cooling magma, water vapor, carbon dioxide, sulfur compounds, immediately disperse into space, leaving the lunar surface naked to the cosmic chill. The cooling process follows the laws of thermodynamics with inexorable precision. The outermost layer of magma begins to solidify first, forming a thin crust of solid rock that floats atop the still molten interior like ice forming on a pond. But this early crust remains fragile, constantly broken and reformed by convection currents in the magma below. Plumes of hot material rise from the depths, crack through the solidifying surface, and spread across the moon's face in slow, glowing rivers that trace geometric patterns visible from Earth. Deep within the molten moon, a subtle process of differentiation begins. Denser minerals, rich in iron and magnesium, sink toward the center under the gentle but persistent pull of lunar gravity. Lighter materials, aluminum-rich feldspars and calcium-bearing plagioclase, rise toward the surface like cream separating from milk. This gravitational sorting will determine the moon's internal structure for billions of years to come, creating distinct layers that tell the story of cooling and crystallization in the language of mineralogy. The magnetic field that surrounds the young moon flickers and strengthens, unlike Earth's powerful magnetosphere, generated by the churning of its large iron core. The moon's magnetic field emerges from the motion of metallic particles suspended throughout the magma ocean. Iron droplets, inherited from both Earth and Theia, swirl through the convecting rock like tiny compass needles, their collective motion generating electrical currents that create magnetic loops and field lines extending into space. This early lunar magnetosphere provides brief protection against the solar wind, streams of charged particles flowing outward from the young sun. When these particles encounter the moon's magnetic field, they deflect around the lunar surface, creating a bow shockwave in the solar plasma. The interaction generates auroras of sorts, ghostly curtains of light that dance across the moon's thin exosphere as solar ions collide with atoms of sodium and potassium vaporized from the cooling rock below. Earth observes this transformation from its position 30,000 miles away. The distance between the two worlds is much smaller than today. The moon orbits closer, appearing 3 times larger in Earth's molten sky than it will to future human observers. Tidal forces between the planets create massive bulges in both magma oceans, great waves of liquid rock that surge back and forth with a rhythm determined by orbital mechanics rather than weather. These tidal interactions serve as a cosmic thermostat, stirring both worlds' interiors and preventing them from cooling too quickly. The moon's magma ocean remains liquid for tens of millions of years, longer than it would in isolation, sustained by the gravitational massage of its planetary companion. Energy flows back and forth between Earth and Moon through tidal heating, an invisible bond that connects the two worlds as intimately as a shared circulatory system. The mystery of the Moon's internal structure emerges during this cooling phase. Unlike terrestrial planets, which typically develop large iron cores, the Moon's metallic center remains proportionally small, only about 20% of the lunar radius. Some scientists theorize that the Moon's iron core composition reflects the selective nature of the impact that created it, suggesting that only the outer layers of Theia and Earth became incorporated into the lunar sphere. Others propose that iron particles remained suspended in the magma ocean longer than expected, creating a more uniform distribution of metals throughout the lunar interior. As the magma ocean gradually solidifies from the outside in, the Moon begins its long transition from a world of liquid fire to one of silent stone. The process unfolds over geological ages, each century adding another thin layer to the growing crust. Different minerals crystallize at different temperatures as the cooling progresses. Plagioclase feldspars solidify first, creating a flotation crust of light-colored rock that rises to the surface. These early crustal rocks will eventually form the lunar highlands, the bright, heavily cratered regions that future observers will see from Earth. The surface temperature drops incrementally from cherry red heat through dull orange glow to the silvery gray radiance that will characterize the Moon for the remainder of cosmic time. The magnetic field begins to weaken as convection slows and metallic particles settle into stable configurations. The random motion that created electrical currents gradually gives way to organized crystalline structures where atoms occupy fixed positions in mineral lattices. Only took 50 million years for the Moon to cool from incandescent liquid to solid rock. Only took the patient radiation of heat into empty space to transform a sphere of fire into the gentle light that will inspire future poets. Only took the laws of thermodynamics, operating without haste or urgency, to create the quiet companion that will watch over Earth through ice ages and mass extinctions, through the rise of life and the dawn of consciousness. Maintaining its vigil with the patience of stone and the memory of molten birth held forever in its crystalline heart. The gravitational dance between Earth and Moon begins the moment both worlds achieve sufficient mass to exert meaningful force upon each other's motion. In the early millennia following their violent birth, the two bodies orbit in a cosmic waltz whose tempo is measured not in beats per minute, but in geological epochs. each revolution taking mere days rather than the month-long cycle that will characterize their mature relationship. The Moon circles Earth at a distance of only 20,000 miles, so close that if our planet possessed rings like Saturn, the Moon would sweep through them like a celestial broom, clearing a gap in the debris through gravitational influence alone. At this intimate distance, tidal forces operate with an intensity that dwarfs anything experienced in the modern Earth-Moon system. These are not the gentle tide pools and shifting shorelines that will one day mark the rhythm of terrestrial oceans, but massive deformations of both worlds' surfaces that stretch and compress the cooling magma with mechanical precision. The Moon's gravity pulls Earth's molten rock into an elongated shape, creating bulges on both the near and far sides that follow the lunar orbit like faithful servants. Similarly, Earth's much stronger gravitational field distorts the Moon into a slight ellipsoid, with the lunar surface rising and falling by hundreds of feet twice each day in a rhythm synchronized with orbital mechanics. These tidal bulges represent the conversion of orbital energy into heat through friction, a cosmic brake system that gradually slows both worlds' rotation and pushes them apart through conservation of angular momentum. Each time the molten rock flows to maintain hydrostatic equilibrium with the changing gravitational field, internal friction generates thermal energy that supplements the heat left over from the formation impacts. The process operates like a planetary massage, kneading both worlds' interiors and maintaining their liquid state for millions of years longer than simple radiative cooling would allow. The young Earth spins on its axis once every 6 hours, completing 4 full day-night cycles in the span of what will later become a single terrestrial day. This frantic rotation creates a world where sunrise follows sunset in rapid succession, where weather patterns, if any existed on the molten surface, would be compressed into abbreviated cycles of heating and cooling. The centrifugal force generated by this rapid spin flattens Earth into an oblate spheroid, bulging at the equator and compressed at the poles like a spinning ball of clay shaped by its own angular momentum. The Moon's influence on this rotation manifests through the same tidal forces that deform both world surfaces. As Earth's tidal bulges attempt to remain aligned with the Moon's position, but are carried slightly ahead by the planet's faster rotation, a torque develops that acts to slow Earth's spin. The energy dissipated through this tidal friction transfers to the Moon's orbital motion, gradually pushing the lunar orbit outward through the conservation laws that govern all motion in the universe. This represents one of the fundamental principles of celestial mechanics, that energy cannot be created or destroyed, only transferred from one form to another through the patient operation of physical law. The Moon experiences its own tidal evolution. Though the process operates through different mechanisms due to the lunar body's smaller size and different internal structure, Earth's gravitational field creates substantial tidal heating within the Moon's magma ocean, generating convection currents that circulate molten rock from the lunar center to its surface. These thermal currents carry heat outward more efficiently than simple conduction, maintaining the magma ocean's liquid state and driving the chemical differentiation that separates heavy minerals from light ones. More significantly, Earth's tidal forces begin the process that will eventually lock one face of the Moon toward our planet permanently. The gravitational gradient across the Moon's diameter, stronger on the Earth-facing side, weaker on the far side, creates a torque that tends to align the Moon's longest axis with the Earth-Moon line. Initially, the Moon rotates independently of its orbital period, presenting different faces to Earth as it spins. But the tidal torque acts like a cosmic brake, gradually slowing the lunar rotation until it matches the orbital period exactly. This synchronous rotation, known as tidal locking, represents the most stable configuration for the Earth-Moon system. Once achieved, it will persist for billions of years, creating the familiar situation where the same lunar hemisphere always faces Earth while the far side remains forever hidden from terrestrial observers. The process unfolds over millions of years, with the moon's rotation period gradually lengthening from hours to days to weeks until it matches the month-long orbital period that characterizes the mature system. The mathematics of tidal evolution follow precise equations derived from Newton's law of universal gravitation and the principles of energy conservation. The tidal force between two bodies varies as the inverse cube of the distance separating them, meaning that small changes in orbital radius create large changes in tidal strength. As the moon spirals outward due to tidal friction, the tidal forces weaken rapidly, causing the rate of further evolution to slow exponentially. This creates a negative feedback loop that stabilizes the system over geological time, preventing the moon from escaping entirely while maintaining the tidal coupling that drove its initial evolution. The early Earth-Moon system experiences tidal forces roughly 100 times stronger than those operating today. These extreme conditions create massive flows of molten rock within both worlds, generating complex convection patterns that mix and homogenize the magma ocean's chemical composition. Iron droplets and silicate crystals circulate through three-dimensional currents that extend from each world's center to its surface, creating a thorough stirring action that prevents the formation of stable chemical gradients during the early cooling phase. The energy dissipated through tidal friction manifests as heat distributed throughout both worlds' interiors. In Earth's case, this tidal heating supplements the thermal energy provided by radioactive decay and residual formation heat, maintaining the planet's molten state and delaying the onset of plate tectonics by millions of years. For the Moon, with its much smaller mass and reduced internal heat budget, tidal heating provides the primary source of thermal energy during the later stages of magma ocean cooling, extending the liquid phase well beyond what would be possible through radiative cooling alone. This thermal coupling between Earth and Moon creates a unique situation in planetary science, two worlds whose geological evolution remains intimately connected through gravitational forces despite their physical separation. The Moon's internal temperature depends not only on its own heat production and loss, but also on the mechanical energy delivered through tidal flexing. Earth's rotation rate and axial stability are influenced by the Moon's orbital evolution and the transfer of angular momentum between the two bodies. The process of tidal locking begins almost immediately after the Moon's formation, but requires millions of years to reach completion. During the intermediate stages, the Moon experiences periods of differential rotation where its surface and interior rotate at slightly different rates. The rigid crust that begins to form as the magma ocean cools cannot keep pace with the changing tidal forces, creating stress fractures and fault systems that will persist long after the synchronous rotation is achieved. These early tidal stresses leave permanent scars in the lunar geology, linear features called tidal bulge fossils that record the orientation of ancient stress fields in the solidifying rock. The pattern of these features provides evidence for the Moon's rotational history and the strength of ancient tidal forces, allowing planetary scientists to reconstruct the evolution of the Earth-Moon system through forensic analysis of lunar surface geology. The Moon's orbit during this early period exhibits significant eccentricity, meaning that its distance from Earth varies substantially during each revolution. At closest approach, called perigee, the Moon swings to within 15,000 miles of Earth's surface. At farthest distance, or apogee, it recedes to nearly 30,000 miles. This elliptical orbit creates periodic variations in tidal strength that cause both worlds' magma oceans to pulse with a complex rhythm determined by orbital mechanics rather than internal geological processes. The gravitational interactions during close approaches generate heating events that temporarily remelt portions of the Moon's solidifying crust. These periodic thermal pulses reset the cooling clock repeatedly, preventing the formation of a stable solid surface for the first several million years of lunar evolution. The Moon exists in a state of thermal oscillation, alternately cooling and reheating as its elliptical orbit brings it closer to and farther from Earth's gravitational influence. The mystery of the Moon's current orbital inclination, tilted about 5 degrees relative to Earth's equatorial plane, may trace its origin to these early gravitational interactions. Computer simulations suggest that the chaotic dynamics of the evolving Earth-Moon system could have excited the lunar orbit into a tilted configuration through resonances with Earth's changing rotation period and axial orientation. The process involves complex three-body interactions between Earth, Moon, and Sun that operate over timescales longer than the cooling of the magma oceans, but shorter than the age of the solar system. As the tidal evolution continues, both worlds begin to settle into more stable configurations. Earth's rotation slows from 6 hours per day toward the 24-hour period that will characterize its mature state. The Moon's orbit expands outward, reducing the tidal forces and allowing both worlds' surfaces to begin cooling without constant tidal reheating. The frantic gravitational coupling of the early system gives way to the more sedate interactions that will govern the Earth-Moon relationship for the remainder of their existence. Only took the patient operation of tidal forces to transform two chaotically spinning worlds into a synchronized binary system, only took the conversion of rotational energy into heat and heat into the outward migration of the Moon to create the stable gravitational partnership that will govern Earth's tides and seasons for billions of years. Only took the mathematics of celestial mechanics, operating with the precision of clockwork scaled up to planetary dimensions, to establish the cosmic dance that will one day allow conscious observers to predict eclipses, navigate by lunar phases, and measure time itself by the patient swing of their celestial companion through the star-filled sky above. As the Moon's magma ocean cools and crystallizes over millions of years, the lighter minerals that have been floating like foam on its molten surface begin to solidify into the first permanent crust. These aluminum-rich feldspars and calcium-bearing plagioclase minerals, with densities lower than the iron-rich materials sinking toward the lunar core, accumulate in a bright shell that will define the Moon's appearance for the remainder of cosmic time. The process resembles the formation of slag on molten metal, except scaled up to encompass an entire world and operating with the patience of geological time. This primitive crust consists almost entirely of a single mineral type, anorthosite, composed of crystals of plagioclase feldspar that form through fractional crystallization as the magma ocean slowly cooled. On Earth, an orthosite occurs only in rare, ancient rock formations that geologists treasure as windows into our planet's earliest history, but on the Moon, an orthosite becomes the dominant crustal rock, creating vast highlands of nearly pure feldspar that reflect sunlight with brilliant efficiency. These anorthosite plains will eventually cover more than 80% of the lunar surface, forming the bright, heavily cratered terrain visible to naked-eye observers as the Moon's lighter regions. The chemistry of an orthosite formation tells the story of the Moon's internal evolution with crystalline precision. As temperatures in the magma ocean drop below 1200 degrees Celsius, plagioclase feldspar becomes the first major mineral to crystallize in large quantities. These early crystals, with their relatively low density of about 2.7 grams per cubic centimeter, rise through the denser magma like bubbles ascending through honey. The process operates slowly, with individual crystals taking thousands of years to migrate from the depths of the magma ocean to its surface. But the cumulative effect over millions of years creates a flotation crust several miles thick. The formation of this anorthositic crust represents one of the most dramatic examples of planetary differentiation in the solar system. Unlike Earth, where plate tectonics constantly recycles crustal material back into the mantle, the Moon's small size and rapid cooling create conditions where the initial differentiation products remain largely undisturbed at the surface, The anorthosite highlands preserve a record of the Moon's magma ocean phase with remarkable fidelity, like a geological fossil of planetary birth frozen in crystalline form. As the flotation crust thickens and solidifies, it begins to insulate the remaining magma ocean below, slowing the cooling process and allowing more complex mineral assemblages to crystallize in the lunar interior. Beneath the anorthosite layer, iron-rich pyroxenes and olivines continue to form and sink toward the center, creating a stratified mantle where mineral composition varies systematically with depth. This chemical layering will influence lunar volcanism for billions of years, determining which types of magma will eventually rise to the surface during later episodes of geological activity. The plagioclase crystals that form the anorthosite highlands grow to remarkable sizes in the low-gravity, low-pressure environment of the cooling magma ocean. Individual feldspar crystals several inches across develop within the slowly crystallizing melt, their faces reflecting light with mirror-like precision. These large crystals, called phenocrysts by petrologists, create the characteristic sparkle visible in lunar highland rocks when examined under artificial illumination. The Apollo astronauts described this effect as giving the lunar surface a diamond-like glitter that no terrestrial rock formation can match. The anorthosite formation process operates through a mechanism that planetary scientists call magma ocean overturn. As the upper portions of the magma ocean crystallize into low-density feldspar, the remaining liquid becomes progressively enriched in iron, magnesium, and other dense components. This residual magma, now denser than the solid crust above it, becomes gravitationally unstable and begins to sink back toward the lunar interior. The downwelling liquid carries with it small amounts of the solid anorthosite, creating a complex convective system that mixes crystalline and molten material throughout the cooling moon. This overturn process helps explain one of the puzzles of lunar geochemistry: the presence of small amounts of iron-rich minerals within the predominantly feldspar-rich highland crust. Computer models suggest that the sinking residual magma creates turbulent mixing that entrains fragments of the anorthosite flotation crust and carries them downward, while simultaneously bringing iron-rich crystals upward from the deeper magma ocean. The result is a highland crust that, while dominated by an orthosite, contains a complex mixture of mineral types that record the chaotic final stages of magma ocean crystallization. The cooling and crystallization of the lunar magma ocean occurs in stages, with different regions solidifying at different rates depending on their depth and thermal environment. The polar regions, which receive less solar heating and radiate heat more efficiently into space, develop solid crusts before equatorial areas. Similarly, the lunar far side, permanently turned away from Earth's radiant heat, cools more rapidly than the near side. These thermal variations create a complex pattern of crystallization that produces subtle but measurable differences in highland rock composition across the lunar surface. As the anorthosite crust thickens to several kilometers, it begins to develop the structural strength necessary to support topographic relief. The first lunar mountains form not through tectonic compression or volcanic construction, but through the differential cooling and contraction of the crystallizing magma ocean. As the moon's interior shrinks during cooling, the rigid crust wrinkles and buckles to accommodate the reduced volume, creating ridge systems and elevated massifs that rise above the surrounding highland plains. These early lunar mountains lack the sharp peaks and dramatic relief of terrestrial mountain ranges formed by plate tectonics or volcanism. Instead, they resemble broad, rolling hills with gentle slopes determined by the flow characteristics of the partially molten crust during its formation. The low lunar gravity allows these features to achieve greater heights relative to their width than would be possible on Earth, creating highland landscapes of subtle but persistent topographic variation. The anorthosite highlands also begin to develop the impact crater population that will become their most distinctive characteristic. Even during the final stages of magma ocean cooling, the inner solar system remains filled with debris from planetary formation, asteroids, comets, and planetesimals that follow chaotic orbits through the space between worlds. When these objects strike the cooling lunar surface, they excavate craters in the newly solidified anorthosite, creating circular scars that expose the bright feldspar bedrock and establish the heavily cratered appearance that will characterize the lunar highlands for billions of years. The largest impacts during this early period create multi-ring basins, enormous circular features hundreds of miles across with concentric rings of uplifted crust surrounding central depressions. These ancient impact structures, formed while the lunar crust remained relatively thin and hot, create some of the moon's most prominent topographic features. The rings result from the elastic rebound of the crust following impact, similar to the ripples created when a stone is dropped into water, except frozen permanently in solid rock. The mystery of the moon's global asymmetry begins to emerge during the anorthosite formation period. For reasons that planetary scientists continue to debate, the lunar far side develops a significantly thicker anorthosite crust than the near side facing Earth. This thickness difference, averaging several kilometers, creates the fundamental geological distinction that will influence all subsequent lunar evolution. The thicker far side crust provides better insulation for the interior magma, while the thinner near side crust allows more efficient heat loss and creates conditions favorable for later volcanic activity. Several theories attempt to explain this crustal asymmetry. One suggests that Earth's gravitational field and radiant heat preferentially thinned the near side crust during its formation. Another proposes that the impact that created the moon imparted a slight asymmetry in the initial distribution of material, with more anorthosite-forming components concentrated on the far side. A third hypothesis involves the capture of a second, smaller moon early in lunar history, whose subsequent impact with the far side added extra thickness to that hemisphere's crust. Recent analysis of lunar samples and orbital data supports a complex origin involving multiple factors. The near-side crust appears to contain a higher concentration of radioactive elements, uranium, thorium, and potassium, that generate additional heat and promote partial melting. This enhanced heat production may have prevented the near-side anorthosite from achieving the same thickness as its far-side counterpart, creating the asymmetry through internal thermal processes rather than external influences. As the final pockets of magma ocean crystallize beneath the completed anorthosite crust, they create small volumes of highly evolved liquid enriched in elements that did not fit easily into the major rock-forming minerals. These residual melts, rich in potassium, rare earth elements, and phosphorus, solidify into unusual rock types called creep basalts, an acronym that captures their distinctive chemistry. These creep-rich regions will later serve as heat sources that drive volcanic activity long after the main magma ocean has solidified, creating localized hotspots in the lunar interior that influence geological processes for billions of years. Only took the slow crystallization of a global magma ocean to create the moon's bright anorthosite highlands. Only took the patient sorting of minerals by density and melting point to establish the chemical foundation for 4 billion years of lunar geological history. Only took the inexorable operation of physical chemistry, working grain by grain through cooling rock, to construct the brilliant crustal shell that reflects Earth light back across the vacuum of space and creates the gentle illumination that will one day guide nocturnal travelers, inspire poets to write of silver beams and gentle radiance, and provide the bright backdrop against which the dark Maria will etch their ancient stories of impacts and volcanic floods in stone. The late heavy bombardment begins approximately 600 million years after the moon's formation, when gravitational instabilities in the outer solar system suddenly unleash a storm of asteroids and comets toward the inner planets, Jupiter and Saturn, settling into orbital resonances that will define their positions for billions of years. Scattered debris from the asteroid belt and Kuiper belt inward like cosmic billiard balls ricocheting through space. The Moon, with no atmosphere to burn up incoming projectiles and no geological activity to erase impact scars, becomes a passive recorder of this celestial violence, its anorthosite highlands accumulating circular wounds that will preserve the memory of bombardment until the end of time. The impactors arrive with velocities ranging from 10 to 70 kilometers per second, carrying kinetic energies equivalent to millions of nuclear weapons. When a 10-kilometer asteroid strikes the lunar surface at cosmic velocity, it excavates a crater 60 kilometers across and several kilometers deep in a matter of seconds. The impact generates temperatures exceeding 10,000 degrees Celsius, instantly vaporizing both the projectile and large volumes of lunar rock. The expanding fireball of superheated plasma rises into the vacuum of space before condensing and falling back as a rain of molten droplets that coat the surrounding landscape with impact glass. These cosmic collisions operate through physics so extreme that normal materials behave like fluids despite their solid state. The anorthosite bedrock flows outward from impact points in concentric waves, creating terraced crater walls and raised rims that freeze permanently in their positions of maximum distortion. The rebound of compressed rock creates central peaks in the largest craters, uplifting material from several kilometers below the surface and exposing the Moon's internal structure like geological cross-sections carved by violence. The largest impacts create multi-ring basins that dominate entire hemispheres of the lunar surface. These enormous structures, hundreds of kilometers across, result from collisions with asteroids the size of small mountains traveling at hypersonic speeds. The Imbrium Basin. Visible to naked eye observers as the right eye of the man in the moon, forms when a 60-kilometer impactor strikes the northwestern lunar surface with energy equivalent to 10 trillion tons of explosive. The impact excavates material to depths of 30 kilometers, exposing ancient rocks from the lower crust and creating shock waves that travel completely through the Moon to emerge on the far side as focused seismic energy. The formation of these giant impact basins follows a sequence that planetary scientists have reconstructed through careful analysis of crater geology and overlapping relationships. The initial contact between projectile and surface creates a transient cavity that expands outward faster than the speed of sound in rock. Shock waves compress the lunar crust to pressures exceeding 1 million atmospheres, transforming familiar minerals into high-pressure phases that exist nowhere else in nature. The cavity continues expanding until gravitational forces overcome the outward momentum, causing the excavated material to collapse back into the depression under lunar gravity. This collapse phase creates the characteristic multiple ring structure of large lunar basins. As the central region rebounds from the extreme compression of impact, it rises above the surrounding terrain like a slow-motion fountain of solid rock. Simultaneously, the crater walls slump inward under their own weight, creating concentric terraces that mark successive episodes of gravitational failure. The interaction between central uplift and rim collapse generates the ring-shaped mountain chains that define basin architecture and create some of the Moon's most spectacular topographic features. The debris ejected by these massive impacts travels in ballistic trajectories that carry lunar material across thousands of kilometers. The largest fragments, hurled completely beyond the Moon's gravitational influence, escape into interplanetary space, where they will eventually strike other worlds or drift in solar orbit as meteoroids. Smaller ejecta follow parabolic paths that return them to the lunar surface at distances determined by their launch velocity and the Moon's weak gravitational field. This secondary cratering creates chains of smaller impacts radiating outward from major basins, painting ray-like patterns across the lunar surface that remain visible for millions of years. The continuous bombardment gradually saturates the lunar highlands with craters of all sizes, from microscopic pits created by cosmic dust to the giant multi-ring basins that reshape entire regions. The surface develops a characteristic size-frequency distribution where small craters vastly outnumber large ones. Following mathematical relationships that reflect the population statistics of impacting debris, this cratered landscape becomes the Moon's dominant topographic signature, creating the pockmarked appearance that distinguishes lunar terrain from the smooth surfaces of atmosphere-bearing planets. Between the major impact events, smaller projectiles continue to strike the lunar surface at rates far exceeding modern bombardment levels. House-sized asteroids arrive every few centuries, creating craters several kilometers across. Car-sized meteoroids impact daily, excavating fresh craters tens of meters in diameter. Even microscopic particles, traveling at hypervelocities through the vacuum of space, constantly sandblast the lunar surface and gradually erode the sharp features created by larger impacts. This continuous cratering creates a layer of fragmented rock called regolith that accumulates across the entire lunar surface. Each impact, regardless of size, shatters local bedrock and mixes the fragments with material excavated from previous craters. The result is a complex soil composed of angular rock chips, impact glass, and mineral grains crushed to microscopic dimensions. The regolith layer grows thicker with time, eventually reaching depths of several meters in highland regions where billions of years of impacts have pulverized the original anorthosite bedrock. The chemistry of impact processes introduces exotic elements to the lunar surface through the projectiles themselves. Metallic asteroids contribute iron and nickel in proportions rarely found in lunar rocks. Comets deliver water ice, organic compounds, and volatile elements that briefly enrich the tenuous lunar atmosphere before escaping to space. The most energetic impacts create local deposits of shocked minerals, diamond, stishovite, and other high-pressure phases that form only under the extreme conditions generated by cosmic collisions. The heat generated by bombardment temporarily remelts portions of the lunar crust, creating pools of impact melt that cool into dark, glassy rocks with compositions reflecting mixtures of local bedrock and projectile material. These impact melts preserve chemical signatures of the bombardment in solidified form, allowing future analysis to determine the types and velocities of ancient impactors. The largest basins contain impact melt deposits hundreds of meters thick, vast lakes of once molten rock that required thousands of years to cool and crystallize completely. The gravitational effects of basin-forming impacts extend far beyond the immediate crater regions. The removal of massive amounts of crustal material creates gravitational anomalies called mascons, concentrations of dense rock that alter the Moon's gravitational field and influence the orbits of spacecraft flying overhead. These mascons result from the inflow of dense mantle material to fill the cavities excavated by the largest impacts, creating positive gravity anomalies that persist for billions of years. The timing of the late heavy bombardment corresponds with a period of orbital instability in the outer solar system as Jupiter and Saturn achieve their final configuration. Computer simulations suggest that this gravitational reorganization scattered debris from stable asteroid belt orbits into highly elliptical trajectories that cross the orbits of the inner planets. The bombardment rate peaked approximately 3.9 billion years ago before declining exponentially as the scattered debris was either captured by planets or ejected from the solar system entirely. The Moon's cratered highlands preserve this bombardment history with remarkable fidelity because lunar geology lacks the erosional and tectonic processes that erase impact features on other worlds. Every crater larger than a few hundred meters in diameter that formed during the late heavy bombardment remains visible today, creating a permanent archaeological record of solar system violence. The overlapping relationships between craters of different ages allow planetary scientists to construct detailed chronologies of impact events and estimate bombardment rates throughout lunar history. The mystery of bombardment selectivity, puzzles researchers who study the distribution of crater sizes and compositions across the lunar surface. Some regions appear to have experienced more intense cratering than others, suggesting either preferential targeting by specific populations of impactors or subsequent geological processes that modified the crater record. The lunar far side, in particular, shows evidence of more intense bombardment than the near side, possibly due to gravitational focusing effects or the protection offered by Earth's gravitational influence. Only took 600 million years of cosmic violence to transform the Moon's smooth anorthosite plains into the heavily cratered wasteland visible today. Only took the gravitational chaos of giant planet migration to unleash the asteroid storm that carved circular scars across every square kilometer of the lunar surface. Only took the patience of airless preservation to maintain this record of ancient bombardment, creating the cosmic museum that will one day allow human observers to reconstruct the violent youth of the solar system by reading the stories written in stone across the Moon's eternal, unchanging face. As the late heavy bombardment wanes and the rain of cosmic debris diminishes to a gentle patter, the largest impact basins begin to fill with dark volcanic rock that will transform the Moon's appearance forever, deep beneath the newly formed craters. The heat generated by massive impacts has partially melted the lunar mantle, creating reservoirs of iron-rich magma that rise slowly toward the surface through the fractured crust. These basaltic melts, denser and darker than the anorthosite highlands, emerge through fissures and volcanic vents to flood the circular depressions with layers of solidified lava that early astronomers will mistake for ancient seas. The Maria, as these dark plains come to be known, represent the Moon's final major episode of geological activity. Unlike the explosive volcanism characteristic of Earth, lunar volcanism proceeds through gentle, effusive eruptions that pour liquid rock across the landscape like slow rivers of fire. The low lunar gravity and lack of atmospheric pressure allow these basaltic flows to spread across vast distances, covering thousands of square kilometers with individual lava flows only a few meters thick. The accumulated layers of these flows eventually reach depths of several kilometers in the deepest basins. The composition of lunar basalts differs significantly from their terrestrial counterparts, reflecting the unique chemistry of the Moon's interior and the specific conditions under which the magmas formed. Lunar basalts contain virtually no water, a consequence of the Moon's formation, through impact processes that vaporized all volatile compounds. They also show enrichment in titanium, iron, and other refractory elements that remained behind when lighter materials were lost to space during the Moon's violent birth. These chemical signatures allow planetary scientists to trace each basalt flow back to its source region deep within the lunar mantle. The timing of mare volcanism correlates closely with the thermal evolution of the Moon's interior. As the initial heat from formation gradually dissipated through radiative cooling, radioactive decay of uranium, thorium, and potassium became the dominant source of internal energy. These radioactive elements, concentrated in the residual melts that crystallized last during magma ocean solidification, created localized hotspots in the lower crust that eventually achieved temperatures sufficient for partial melting. The resulting magmas, less dense than the surrounding solid rock, began their slow ascent toward the surface through whatever pathways the fractured crust provided. The giant impact basins serve as preferential sites for volcanic eruption because their formation process created deep fractures that penetrate through the entire thickness of the lunar crust. These impact-generated fault systems provide conduits through which ascending magma can reach the surface without having to force its way through solid rock. Additionally, the gravitational anomalies created by basin formation focus stress fields in ways that promote further fracturing and maintain open pathways for volcanic transport. Mare Imbrium, the largest and most prominent of the lunar seas, begins filling with basaltic lava approximately 3.8 billion years ago. roughly 100 million years after the impact that created the basin itself. The volcanism proceeds in episodes separated by millions of years, with each eruptive phase adding new layers to the growing lava plain. The earliest flows emerge from multiple vents around the basin's periphery, gradually coalescing into a continuous sheet of dark rock that drowns the inner ring mountains and creates the smooth surface visible to terrestrial observers. The individual lava flows that create the Moriah exhibit remarkable uniformity in thickness and composition, suggesting eruption from well-mixed magma chambers deep in the lunar interior. Unlike terrestrial volcanic systems, where magma chemistry can vary dramatically during single eruptions due to crustal contamination and fractional crystallization, lunar basalts maintain consistent compositions over enormous volumes. This uniformity reflects the moon's simple internal structure and the absence of the complex crustal recycling processes that characterize Earth's volcanic systems. The cooling and solidification of mare basalts proceed according to the same physical principles that govern terrestrial lava flows, but with important modifications due to the lunar environment. The absence of atmospheric convection means that cooling occurs primarily through thermal radiation, creating temperature gradients that differ substantially from those experienced by earthbound lavas. The low lunar gravity allows gas bubbles dissolved in the magma to rise more slowly through the cooling liquid, creating vesicular textures with distinctive patterns of spherical cavities. As each basaltic flow cools from its initial temperature of approximately 1200 degrees Celsius, it develops a characteristic internal structure with a glassy upper crust, a crystalline interior, and a lower zone enriched in dense minerals that settled under lunar gravity. This layered architecture, repeated in thousands of individual flows throughout each mare basin, creates the complex stratigraphy that future missions will reveal through drilling and seismic analysis. The surface textures of cooled basalt flows preserve detailed records of the eruption conditions under which they formed. Smooth, rope-like textures called pahoeho develop when lavas flow slowly and maintain high temperatures during emplacement. Rough, clinker-like surfaces known as AA form when flows move more rapidly or cool quickly during transport. The distribution of these different texture types across mare surfaces provides clues about eruption rates, lava temperatures, and the topographic gradients that controlled flow directions during emplacement. Between major eruptive episodes, the partially filled basins experience impact cratering that excavates holes in the solidified lava flows and exposes the underlying rock layers. These post-mare craters provide natural cross-sections through the volcanic stratigraphy, allowing remote analysis of lava flow sequences without the need for drilling. The size-frequency distribution of craters on different mare surfaces also serves as a relative dating technique, with fewer craters indicating younger volcanic surfaces. The gradual decline of mare volcanism over time reflects the moon's inexorable cooling and the depletion of radioactive heat sources in the lunar interior. The youngest mare basalts, found primarily in Oceanus Procellarum and Mare Imbrium, solidified approximately 3.2 billion years ago. After this point, the moon's internal temperature dropped below the threshold necessary for significant partial melting, effectively ending the era of major volcanic activity and leaving the moon in the geologically quiescent state that characterizes its modern condition. The chemical diversity of mare basalts reveals the complex thermal and compositional structure of the lunar interior during the volcanic period. High titanium basalts, enriched in the mineral ilmenite, appear to originate from source regions that incorporated materials from the final stages of magma ocean crystallization. Low titanium basalts derive from deeper mantle sources that escaped significant contamination by late-stage melts. These compositional variations create subtle color differences in mare surfaces that are detectable through careful telescopic observation and spacecraft photography. The distribution of mare volcanism shows a pronounced asymmetry between the lunar near side and far side, with the vast majority of basaltic plains occurring on the hemisphere that faces Earth. This asymmetry reflects the crustal thickness variations established during the Moon's formation, with the thinner near-side crust providing easier pathways for magma ascent, while the thicker far-side crust effectively blocked most volcanic eruptions. The few small maria that do occur on the far side occupy the deepest impact basins where the crustal thickness approaches near-side values. The mystery of lunar volcanic glass beads discovered in mare basalt samples reveals episodes of explosive volcanism that contrast sharply with the predominantly effusive nature of most mare eruptions. These microscopic glass spheres, formed through fire fountain eruptions driven by the rapid expansion of dissolved gases, indicate that some lunar magmas contain sufficient volatile compounds to generate explosive activity despite the Moon's generally dry composition. The source of these volatiles remains debated, with possibilities including solar wind implantation, comet impacts, or indigenous lunar hydrogen. Only took 2 billion years of episodic volcanism to fill the Moon's largest impact scars with dark basaltic rock. Only took the slow decay of radioactive elements deep in the lunar interior to melt sufficient rock for creating the smooth plains that dominate the near-side landscape. Only took the patient cooling of countless individual lava flows to construct the dark seas that give the Moon its distinctive mottled appearance and create the facial features that human observers will recognize as the man in the Moon, forever frozen in volcanic stone beneath the silver light of earthshine. The inexorable force of tidal friction continues its patient work across geological ages, gradually slowing the Moon's rotation until one hemisphere locks permanently toward Earth while the other remains forever hidden from terrestrial view. This process of synchronous rotation, operating through the same gravitational mechanics that raised massive tides in the ancient magma oceans, represents one of the most profound transformations in the Moon's orbital evolution. The transition unfolds over hundreds of millions of years, with the lunar days slowly lengthening from hours to weeks to months until it matches the orbital period exactly, initially. The Moon spins independently of its orbital motion, presenting different faces to Earth as it rotates through cycles lasting only a few hours. But Earth's gravitational field creates a subtle asymmetry in the tidal forces acting on the Moon's slightly non-spherical mass distribution. The lunar body, deformed into a slight prolate ellipsoid by its own rotation and Earth's tidal influence, experiences differential gravitational attraction that tends to align its longest axis with the Earth-Moon line. This torque acts like a cosmic brake, gradually transferring rotational energy into orbital energy through the conservation principles that govern all celestial motion. The physical mechanism driving tidal locking operates through internal friction within the Moon's partially molten interior, as Earth's gravity raises tidal bulges in the lunar body. These deformations must migrate around the Moon to follow the changing direction of the gravitational field as the Moon rotates. The viscous drag associated with this tidal flexing dissipates rotational energy as heat, slowly reducing the Moon's spin rate while simultaneously transferring angular momentum to the orbital motion and pushing the Moon outward to greater distances from Earth. During the intermediate stages of this process, the Moon experiences complex rotational dynamics that create varying librations, apparent wobbling motions that allow terrestrial observers to glimpse slightly beyond the geometric limb of the lunar disk. These librations result from the mismatch between the Moon's gradually slowing rotation period and its orbital period, which itself varies due to the elliptical shape of the lunar orbit. When the Moon moves faster than average in its orbit during close approach to Earth, its rotation lags behind the orbital motion, revealing portions of the trailing hemisphere. Conversely, when orbital velocity decreases near apogee, the rotation leads the orbital position, exposing regions of the leading hemisphere. The achievement of perfect synchronous rotation requires precise matching between rotational and orbital periods to within fractions of a second over thousands of years. The final approach to this locked state proceeds asymptotically, with the remaining mismatch becoming smaller and smaller as tidal friction continues to fine-tune the system. During the last few million years before perfect locking, the Moon experiences regular oscillations in its rotation rate as gravitational forces attempt to establish the final equilibrium configuration. The consequences of tidal locking extend far beyond simple rotational dynamics to influence the Moon's geological and thermal evolution in fundamental ways. The permanent division of the lunar surface into Earth-facing and space-facing hemispheres creates distinctly different environmental conditions on each side. The near side receives continuous illumination from Earthshine, reflected sunlight from Earth's surface that provides a gentle but persistent source of heating during the lunar night. The far side, perpetually turned away from this Earthlight, experiences more extreme temperature variations and remains generally cooler than its Earth-facing counterpart. This thermal asymmetry influences the distribution of volatile compounds across the lunar surface. Water ice and other frozen gases, delivered by comet impacts throughout lunar history, tend to accumulate preferentially in permanently shadowed regions near the lunar poles and in the deeper craters of the far side. The near side's warmer average temperatures, enhanced by Earthshine heating, promote the sublimation and loss of these volatile materials, creating a systematic chemical difference between the two hemispheres that spacecraft missions will eventually detect and map in detail. The tidal locking process also affects the Moon's internal structure through the permanent deformation required to maintain the locked configuration. The Moon's solid interior assumes a slightly egg-shaped form with the pointed end directed toward Earth, creating a frozen bulge that reflects the ancient tidal forces responsible for the synchronous rotation. This permanent deformation influences the Moon's gravitational field and creates subtle but measurable variations in the strength of gravity measured by orbiting spacecraft. The mascons, gravitational anomalies associated with the large impact basins, become particularly prominent features of the Moon's gravity field after tidal locking is achieved. The preferential location of most major basins on the Earth-facing hemisphere, combined with their permanent orientation toward our planet, creates a stable pattern of gravitational irregularities that affects the orbits of natural debris and future artificial satellites. These gravity variations concentrate cosmic dust and small meteoroids in specific orbital zones, creating a complex architecture of particle populations around the Moon. The establishment of synchronous rotation fundamentally alters the Moon's relationship with the solar wind, the stream of charged particles flowing outward from the Sun at supersonic speeds. Before tidal locking, all parts of the lunar surface experienced equal exposure to this particle bombardment as the Moon rotated through the solar wind flow. After locking, however, the leading hemisphere of the Moon's orbit receives preferential exposure to solar wind particles, while the trailing hemisphere remains partially shielded by the wake created as the Moon moves through the particle stream. This asymmetric solar wind exposure creates systematic differences in surface chemistry between leading and trailing hemispheres that accumulate over billions of years. Solar wind particles, primarily hydrogen and helium nuclei, implant themselves in the crystal lattices of surface minerals and gradually alter their composition and optical properties. The leading hemisphere develops a characteristic reddish coloration due to the formation of nanoscopic iron particles created by solar wind sputtering, while the trailing hemisphere retains more of its original mineralogical signature. The far side of the Moon, permanently hidden from Earth, evolves into one of the most pristine environments in the inner solar system. Shielded from terrestrial radio interference and protected from the bulk of Earth's magnetospheric particles, the lunar far side preserves conditions representative of the early solar system with remarkable fidelity. The regolith on the far side contains a more complete record of ancient solar wind composition and cosmic ray bombardment, making it an invaluable archive for understanding the Sun's long-term evolution and the galactic environment in which the solar system formed. The achievement of synchronous rotation also stabilizes the Moon's orbital plane and reduces the chaotic variations in lunar motion that characterized earlier epochs. With one hemisphere permanently locked toward Earth, gravitational interactions between the two bodies become more predictable and systematic. The Moon's orbit settles into a configuration where secular perturbations average out over time, creating the stable, predictable motion that will eventually allow human civilizations to develop accurate calendars and predict eclipses centuries in advance. The librations that persist even after perfect tidal locking provide the only means by which terrestrial observers can glimpse portions of the lunar far side without space travel. These apparent wobbling motions, caused by the elliptical shape of the Moon's orbit and the slight inclination of its equatorial plane, allow views of approximately 59% of the lunar surface from Earth over the course of many years. The remaining 41% remains permanently hidden until the advent of spacecraft capable of traveling beyond the Moon's limb. The mystery of the Moon's slight orbital inclination relative to Earth's equatorial plane may trace its origin to the complex dynamics operating during the tidal locking process. Computer simulations suggest that gravitational interactions with the Sun during the locking period could have excited the lunar orbit into its current tilted configuration through resonant coupling between Earth's obliquity and the Moon's changing rotational dynamics. This inclination contributes to the libration effects and ensures that the boundary between visible and hidden hemispheres shifts gradually over time. Only took several 100 million years of tidal friction to transform the Moon from an independently spinning world into Earth's perfectly synchronized companion. Only took the patient dissipation of rotational energy through internal heating to achieve the precise orbital mechanics that will govern the Earth-Moon system for billions of years. Only took the inexorable operation of celestial mechanics, working through the subtle asymmetries of gravitational attraction, to create the eternal partnership between two worlds that will one day inspire poets to write of faithful companionship and allow astronomers to use the Moon as a stable platform for observing the universe beyond. With the Moon now locked in synchronous rotation, its gravitational influence begins to stabilize Earth's chaotic axial motion and establish the climatic predictability that will prove essential for the eventual evolution of complex life. Before the Moon's formation, Earth wobbled through space like a spinning top losing momentum, its rotational axis wandering across a range of angles that created wildly unstable seasons and prevented the establishment of reliable climate patterns. The gravitational torque exerted by the massive lunar companion gradually dampens these chaotic variations, anchoring Earth's axial tilt at the stable 23.5-degree angle that defines our planet's seasonal rhythm. The physics of this stabilization operate through the same tidal mechanisms that locked the Moon's rotation, but apply to the more subtle problem of controlling Earth's orientation in space. The Moon's orbit, inclined about 5 degrees to Earth's equatorial plane, creates a gravitational torque that acts on our planet's equatorial bulge, the slight flattening caused by Earth's rotation. This torque tends to pull Earth's rotational axis into alignment with the orbital plane, but the gyroscopic effect of Earth's spin resists this alignment, creating a compromise equilibrium that maintains the axial tilt at its current value. Without the Moon's stabilizing influence, computer simulations suggest that Earth's obliquity would vary chaotically between 0 and 85 degrees over time scales of millions of years. Such extreme variations would create climate conditions ranging from perpetual global winter, when the axis points nearly perpendicular to the orbital plane, to catastrophic seasonal extremes, when high obliquity causes each hemisphere to experience months of continuous sunlight followed by months of darkness. The presence of the Moon constrains these variations to less than 2 degrees, ensuring that Earth's climate remains within bounds compatible with stable atmospheric and oceanic circulation. The Moon's influence on terrestrial climate extends beyond axial stabilization to encompass the complex dynamics of Earth's orbital evolution. The tidal friction that slows Earth's rotation and pushes the Moon outward also affects the shape of Earth's orbit around the Sun, contributing to the subtle variations in eccentricity and orbital orientation that drive long-term climate cycles. These Milankovitch cycles, operating over tens of thousands of years, create the Ice Age rhythms that will eventually sculpt Earth's surface geography and influence the evolutionary pressures acting on terrestrial life. As the Moon recedes from Earth due to tidal friction, its gravitational influence on our planet's rotation gradually weakens. The process operates so slowly that the Moon retreats only a few centimeters per year, roughly the rate at which fingernails grow. But the cumulative effect over billions of years amounts to substantial changes in the Earth-Moon system. Early in Earth's history, when the Moon orbited much closer to our planet, tidal forces were strong enough to lock Earth's rotation period at only 6 hours. As the Moon withdrew to greater distances, these forces weakened, allowing Earth's rotation to slow toward the 24-hour day that characterizes the modern system. This gradual increase in day length has profound implications for atmospheric and oceanic circulation patterns on Earth. The Coriolis effect, which deflects moving fluids due to planetary rotation, varies inversely with the rotation period. When Earth spun every 6 hours in its youth, the Coriolis effect was 4 times stronger than today, creating atmospheric circulation cells that were smaller and more numerous than modern patterns. As the day length increased with lunar recession, these circulation patterns evolved toward larger, more stable configurations that better support global weather systems and climate stability. The tidal influence of the Moon on Earth's oceans represents one of the most visible manifestations of gravitational coupling between the two worlds. Unlike the ancient tidal forces that operated on molten rock during the magma ocean phase, modern oceanic tides involve the relatively gentle twice-daily rise and fall of liquid water in response to the changing gravitational field as the Moon orbits Earth. These water tides, though much smaller in amplitude than their molten predecessors, play crucial roles in mixing ocean waters, driving coastal ecosystems, and dissipating the orbital energy that continues to push the Moon away from Earth. The mathematics of oceanic tides reveal the complex interplay between lunar and solar gravitational forces that create the familiar pattern of high and low tides experienced at coastal locations. The Moon's proximity makes it the dominant tidal influence despite its smaller mass compared to the Sun. But the solar contribution creates the spring-neap tide cycle where tidal ranges vary predictably over the course of each month. When the Moon and Sun align during new and full moon phases, their gravitational forces combine to create the highest tides. When they pull at right angles during quarter moon phases, their effects partially cancel, producing the lowest tidal ranges. The energy dissipated through oceanic tidal friction amounts to approximately 3.7 terawatts, roughly twice the total electrical power generation capacity of human civilization. This energy, extracted from Earth's rotational motion through the gravitational coupling with the Moon, gradually slows our planet's spin and transfers angular momentum to the lunar orbit. The process operates with mechanical precision, governed by the conservation laws that ensure energy can neither be created nor destroyed, only transformed from one form to another through the patient operation of physical law. The retreat of the Moon also influences the frequency and characteristics of solar eclipses as viewed from Earth's surface in the distant past, when the Moon orbited closer to Earth and appeared larger in the sky. All solar eclipses were total eclipses that completely blocked the Sun's disk for extended periods. As the Moon recedes, its apparent size gradually decreases until it can no longer completely cover the Sun during eclipses. This transition point, where total eclipses become impossible, will occur approximately 600 million years in the future, marking the end of one of Earth's most spectacular astronomical phenomena. The Moon's stabilizing influence on Earth's climate creates what planetary scientists call the habitable zone effect, the maintenance of surface conditions within the narrow range of temperatures where liquid water can exist. Without lunar stabilization, Earth's chaotic obliquity variations would periodically freeze or boil away the oceans, preventing the sustained presence of liquid water necessary for life's emergence and evolution. The Moon thus serves as a cosmic thermostat, maintaining Earth's climate within the bounds necessary for biological processes over geological timescales. Recent research suggests that the Moon's influence on Earth's magnetic field may also contribute to long-term climate stability. The tidal heating generated by lunar gravitational forces helps maintain convection currents in Earth's liquid iron core, sustaining the magnetic dynamo that creates our planet's protective magnetosphere. This magnetic field shields Earth's atmosphere from erosion by the solar wind, preventing the gradual loss of water vapor and other volatile compounds that would otherwise escape to space over billions of years. The precession of Earth's rotational axis, caused by the combined gravitational influences of the Moon and Sun acting on our planet's equatorial bulge, creates a 26,000-year cycle that slowly shifts the orientation of Earth's axis relative to the background stars. This precession affects the timing of seasons relative to Earth's orbital position, creating long-term changes in the distribution of solar heating between hemispheres. The Moon's contribution to this precession helps regulate the amplitude and timing of these variations, preventing extreme shifts that could destabilize global climate patterns. The mystery of Earth's anomalously large Moon compared to other terrestrial planets may reflect the specific collision circumstances that created the Earth-Moon system. Venus, Mars, and Mercury lack substantial satellites capable of providing similar axial stabilization, which may explain their less hospitable climates and reduced potential for supporting complex life. Earth's possession of a large, nearby moon may represent a rare cosmic coincidence that creates uniquely favorable conditions for biological evolution. The long-term evolution of the Earth-Moon system points toward a distant future when tidal friction will eventually synchronize Earth's rotation with the lunar orbital period, creating a configuration where the same terrestrial hemisphere always faces the Moon. This double tidal locking, similar to the system currently observed in the Pluto-Charon system, will occur approximately 50 billion years in the future, long after the Sun has exhausted its nuclear fuel and evolved beyond its current main sequence phase. Only took the patient gravitational influence of Earth's oversized satellite to transform our planet from a chaotically wobbling world into one with stable, predictable seasons. Only took the subtle torque exerted by lunar gravity on Earth's equatorial bulge to prevent the extreme obliquity variations that would sterilize planetary surfaces through climate chaos. Only took the cosmic accident of the Moon's formation to provide Earth with the axial anchor necessary for maintaining the climatic stability that will eventually allow life to emerge from primordial oceans, evolve through countless generations of increasing complexity, and ultimately develop the consciousness necessary to understand the very gravitational dance that made its existence possible. Over billions of years of patient bombardment, the accumulated debris from countless impacts gradually builds a layer of fragmented rock across the entire lunar surface. This regolith, as planetary scientists term this cosmic soil, forms through the relentless grinding action of meteoroids ranging in size from microscopic dust grains to house-sized boulders, each impact shattering local bedrock and mixing the fragments into an increasingly fine-grained blanket that covers mountains, plains, and craters alike. The process operates with the mechanical precision of a planetary mill, pulverizing solid rock into particles ranging from boulder-sized chunks down to microscopic grains finer than flour. The formation of lunar regolith differs fundamentally from soil formation on Earth, where biological, chemical, and atmospheric processes break down rock through weathering and erosion over relatively short timescales. On the airless Moon, mechanical fragmentation through impact provides the only significant means of reducing solid rock to smaller particles. Each meteoroid strike, regardless of size, contributes to this slow disintegration by crushing mineral grains, creating new fractures in bedrock, and dispersing the resulting fragments across the surrounding landscape through ballistic trajectories governed by lunar gravity. The thickness of regolith varies systematically across the lunar surface, reflecting the age and bombardment history of different geological units. The ancient highland regions, exposed to cosmic bombardment for over 4 billion years, accumulate regolith layers averaging 10 to 15 meters in depth. The younger mare surfaces, protected by basaltic lava flows until relatively recently in lunar history, develop thinner regolith deposits typically ranging from 2 to 8 meters deep. These thickness variations create a geological record of bombardment intensity that allows planetary scientists to estimate the age of lunar surface features through regolith depth measurements. The composition of regolith reflects the complex mixing processes that operate during impact events of all scales. Large impacts excavate material from depths of several kilometers, bringing deep crustal rocks to the surface and distributing them across thousands of square kilometers. Smaller impacts create local mixing on meter scales, blending fragments from different rock types into homogeneous mixtures. The cumulative effect over geological time creates regolith compositions that represent averages of the local bedrock chemistry, with individual grains preserving microscopic samples of rocks that may have originated hundreds of kilometers away. Within this mechanical chaos, the solar wind introduces its own subtle chemical signature to the regolith through continuous bombardment by charged particles flowing outward from the sun. Hydrogen and helium nuclei, accelerated to velocities of several hundred kilometers per second, implant themselves in the crystal lattices of surface minerals and gradually alter their composition and optical properties. This space weathering process darkens and reddens the regolith over time, creating the distinctive spectral signature that distinguishes mature lunar soil from fresh rock exposures and allows remote sensing to estimate surface ages. The micrometeorite bombardment that dominates regolith formation operates continuously at rates far exceeding the occasional large impacts that create new craters. Particles smaller than a millimeter in diameter strike the lunar surface billions of times per day, each impact vaporizing a tiny volume of rock and redepositing the condensed vapor as microscopic glass spherules throughout the regolith. These glass beads, ranging in size from nanometers to millimeters, constitute a significant fraction of mature lunar soil and preserve chemical signatures of both the impacting particles and the target rocks they struck. The absence of atmospheric protection means that even the smallest cosmic particles reach the lunar surface at their full interplanetary velocities, typically ranging from 10 to 70 kilometers per second. At these hypervelocities, the kinetic energy of impact exceeds the binding energy of crystal lattices, causing instantaneous melting and vaporization even for dust grains too small to be visible to the naked eye. The shock waves generated by these microscopic impacts propagate through the regolith, causing additional fracturing and grain comminution that extends the mechanical effects far beyond the immediate impact site. The regolith develops a characteristic structure with depth, reflecting the complex history of burial and excavation that affects each particle throughout its residence at the lunar surface. The uppermost few centimeters, directly exposed to micrometeorite bombardment and solar wind irradiation, contain the most mature and space-weathered components. Deeper layers preserve less altered material that was buried by more recent impact deposits, creating a stratigraphy that records the bombardment history and allows reconstruction of ancient impact rates through detailed analysis of regolith cores. Electrostatic forces generated by solar wind charging and photoemission create unusual behaviors in the finest regolith particles, particularly during the sharp transitions between lunar day and night. As the sun sets over a lunar landscape, the sudden cessation of photoemission allows the regolith to develop strong negative charges that can levitate dust particles above the surface through electrostatic repulsion. These dust fountains, invisible to optical observation but detectable through their effects on spacecraft instruments, create a tenuous atmosphere of charged particles that follows the terminator as it sweeps across the lunar surface. The composition of regolith varies with geographical location, reflecting the different bedrock types exposed at the surface and the complex patterns of ejecta dispersal from major impact events. Highland regolith consists primarily of fragmented anorthosite with its characteristic white color and high albedo. Mare regolith derives from dark basaltic rocks and exhibits the low reflectance and neutral coloration typical of iron-rich volcanic materials. Mixed regions near the boundaries between highlands and maria contain complex blends of both rock types, creating intermediate compositions that record the ballistic mixing processes operating during basin-forming impacts. The discovery of water ice within permanently shadowed regolith deposits represents one of the most significant findings of modern lunar exploration. These volatile compounds, delivered by comet impacts throughout lunar history, accumulate in polar craters where temperatures remain below the sublimation point of water ice for billions of years. The regolith in these regions serves as a cold trap, preserving not only water but also other volatile species including carbon dioxide, ammonia, and various organic compounds that provide chemical records of early solar system conditions. The gardening effect of impact bombardment ensures that regolith particles experience multiple cycles of burial and re-excavation throughout their surface residence times. Computer simulations suggest that typical regolith grains are buried to depths of several meters and then re-exposed hundreds of times over periods of millions of years. This constant turnover homogenizes the regolith composition and exposes all particles to space weathering processes, creating the uniform chemical and optical properties characteristic of mature lunar soil. The magnetic properties of regolith particles preserve records of ancient lunar magnetic fields that existed during the Moon's early history, when its core was still hot enough to generate a dynamo. Iron-bearing minerals in impact-melted regolith components acquired thermoremanent magnetization as they cooled in the presence of these ancient fields, creating permanent magnetic signatures that persist billions of years after the lunar dynamo ceased operation. Analysis of these magnetic records allows reconstruction of the timing and intensity of lunar magnetic field generation during the first billion years of lunar evolution. The thermal properties of regolith create the extreme temperature variations experienced at the lunar surface, where daytime temperatures can exceed 120 degrees Celsius, while nighttime temperatures drop below -170 degrees Celsius. The low thermal conductivity of the loosely packed, vacuum-surrounded regolith grains means that heat penetrates only a few centimeters below the surface during the 2-week lunar day, creating a sharp temperature gradient that preserves subsurface ice deposits and affects the chemistry of volatile compounds throughout the regolith column. The mechanical properties of regolith strongly influence the behavior of vehicles and equipment operating on the lunar surface. The fine-grained, cohesionless nature of mature regolith creates soil mechanics similar to dry sand, but with important modifications due to the angular shape of impact-generated particles and the absence of moisture or atmospheric pressure. These properties affect everything from astronaut mobility to the stability of scientific instruments, requiring specialized engineering solutions for successful lunar surface operations. The optical properties of regolith determine the Moon's overall brightness and color as viewed from Earth, creating the familiar silvery appearance that has inspired human imagination throughout recorded history. The complex scattering behavior of regolith particles, modified by space weathering and the presence of microscopic iron particles, produces the characteristic opposition surge that causes the full moon to appear disproportionately bright compared to other lunar phases. This scattering behavior also creates the subtle color variations visible across the lunar surface that allow remote identification of different geological units. The mystery of regolith transport mechanisms on the airless moon puzzles scientists who observe evidence for horizontal movement of fine particles across distances of hundreds of meters. Possible explanations include electrostatic levitation during eclipse events, seismic shaking from meteorite impacts, and thermal cycling effects that cause expansion and contraction of regolith deposits. Understanding these transport processes is crucial for predicting the long-term stability of future lunar installations and the preservation of scientific equipment deployed on the surface. Only took 4 billion years of patient cosmic bombardment to grind solid lunar bedrock into the fine gray powder that coats every square meter of the moon's surface. Only took the accumulated impacts of countless meteoroids, from microscopic dust to mountain-sized asteroids, to create the regolith blanket that preserves chemical records of solar system evolution in its microscopic components. Only took the relentless mechanical grinding of airless space to transform a world of solid rock into one draped in cosmic soil, creating the soft gray landscape that will cushion the footsteps of future explorers and preserve their tracks unchanged for millions of years in the patient silence of lunar time. As the moon ages and cools, the small iron core that formed during the differentiation of the ancient magma ocean gradually loses its ability to generate the magnetic field that once provided modest protection against solar wind bombardment. The lunar dynamo, never as powerful as Earth's due to the moon's smaller size and iron-poor composition, operates through convection currents in liquid metallic core material heated by radioactive decay and tidal friction. But the moon's rapid cooling rate, accelerated by its small size and efficient heat loss through surface radiation, ensures that this magnetic field generation ceases relatively early in lunar history. The physics of magnetic field generation in planetary cores requires specific conditions of temperature, composition, and convective motion that become increasingly difficult to maintain as a world cools. The moon's core, with a radius of only about 400 kilometers compared to Earth's 3 500-kilometer core, contains insufficient radioactive elements to sustain long-term heating. Additionally, the moon's synchronous rotation eliminates the rapid spin that helps drive convective mixing in larger planetary dynamos, reducing the efficiency of magnetic field generation even when adequate thermal energy remains available. Evidence for the ancient lunar magnetic field comes from magnetized rocks collected during Apollo missions and from orbital measurements of remnant magnetization in lunar crustal rocks. These magnetic signatures, preserved in iron-bearing minerals that locked in their magnetization as they cooled below the Curie temperature in the presence of an ambient magnetic field, indicate that the moon possessed a substantial magnetosphere for at least the first 500 million years of its existence. The strength of this ancient field, estimated at between 1 and 100 microtesla, was comparable to Earth's modern magnetic field strength at its surface. The gradual weakening and eventual disappearance of the lunar magnetic field occurs over hundreds of millions of years as the moon's core temperature drops below the threshold necessary for maintaining liquid convection. Computer simulations suggest that the lunar dynamo operated most strongly during the period from 4.2 to 3.5 billion years ago, coinciding with the era of late heavy bombardment and early mare volcanism. The magnetic field then declined steadily, finally ceasing altogether approximately 3.0 billion years ago when the core solidified completely. The loss of magnetic protection exposes the lunar surface directly to the full intensity of solar wind bombardment, fundamentally altering the space weathering processes that modify surface materials. Without a magnetosphere to deflect charged particles, the solar wind strikes the lunar surface at full velocity, implanting hydrogen and helium nuclei directly into mineral grains and creating the characteristic darkening and reddening effects that distinguish mature regolith from fresh rock exposures. This enhanced space weathering rate accelerates after magnetic field loss, creating more pronounced optical changes in surface materials. The absence of a lunar magnetic field also allows solar wind particles to penetrate more deeply into the regolith, creating chemical reduction reactions that produce nanoscopic metallic iron particles throughout the soil column. These tiny iron grains, invisible individually but collectively responsible for the moon's dark appearance and distinctive spectral signature, form through the breakdown of iron-bearing silicate minerals under continuous proton bombardment. The process operates most efficiently in the absence of magnetic shielding, making post-dynamo regolith significantly darker than materials that formed when magnetic protection was available. The timing of magnetic field loss correlates with other major changes in lunar evolution, including the waning of mare volcanism and the transition from active to passive geological processes. The same thermal evolution that shuts down the core dynamo also reduces internal heat generation below the threshold necessary for significant partial melting in the lunar mantle. This synchronization suggests that the moon's magnetic history and volcanic history are intimately connected through the thermal state of the interior, with both processes depending on the same heat sources and cooling mechanisms. Regional variations in the strength and timing of magnetic field loss create complex patterns of remnant magnetization across the lunar surface. Some areas, particularly those associated with large impact basins, preserve strong magnetic signatures that persist billions of years after the global dynamo ceased operation. These magnetic anomalies may result from the concentration of iron-rich impactor material in basin deposits, or from the amplification of weak ambient fields through the shock processes associated with large impacts. The interaction between solar wind and these remnant magnetic anomalies creates miniature magnetospheres that provide localized protection for underlying surface materials. Spacecraft observations reveal that regions with strong crustal magnetization experience reduced space weathering rates, preserving more of their original optical properties than surrounding areas exposed to direct solar wind bombardment. These magnetic mini-magnetospheres also deflect solar wind particles in ways that create complex plasma physics phenomena observable by orbiting instruments. The loss of the global magnetic field affects the moon's thin exosphere by allowing solar wind particles to interact directly with surface materials and liberate atoms through sputtering processes. Without magnetic protection, the rate of atmospheric loss increases dramatically, preventing the accumulation of substantial gas densities even in regions where volcanic outgassing or impact vaporization temporarily enriches the local atmosphere. The modern lunar exosphere, with surface densities less than 1/trillionth that of Earth's atmosphere, represents the equilibrium between continuous particle liberation and escape to space. The chemical signature of solar wind implantation becomes the dominant space weathering process affecting lunar surface materials after magnetic field loss. Hydrogen atoms, comprising the majority of solar wind particles, accumulate in regolith grains to concentrations of several hundred parts per million, creating a substantial reservoir of potentially useful volatiles distributed throughout the lunar soil. This implanted hydrogen can combine with oxygen in silicate minerals to form water molecules, contributing to the trace amounts of water detected in lunar regolith samples. The disappearance of magnetic shielding also allows cosmic rays, high-energy particles from galactic sources, to penetrate more easily into lunar surface materials. These energetic particles create distinctive nuclear reaction products in regolith minerals, including rare isotopes and cosmogenic nuclides that serve as chronometers for measuring surface exposure ages. The enhanced cosmic ray flux after magnetic field loss increases the production rates of these isotopes, creating temporal markers that allow dating of geological events throughout lunar history. The mystery of magnetic field reactivation episodes during the Moon's later history challenges simple models of steadily declining dynamo activity. Some magnetized lunar samples appear to have acquired their magnetization billions of years after the main dynamo ceased operation, suggesting either temporary reactivation of core convection or the generation of magnetic fields through alternative mechanisms such as impact-generated plasma interactions or thermoelectric effects in cooling impact melt sheets. Recent theoretical work suggests that the lunar magnetic field may have experienced multiple episodes of weakening and strengthening in response to changes in core mantle boundary conditions and variations in tidal heating rates as the Moon's orbital distance from Earth evolved. These cyclical magnetic field variations, if confirmed by future sample analysis, would indicate a more complex thermal and magnetic evolution than previously recognized, with implications for understanding magnetic field generation in other small planetary bodies. The study of lunar magnetic field history provides crucial insights into the thermal evolution and internal dynamics of small rocky worlds throughout the solar system. The Moon serves as an accessible laboratory for understanding how planetary magnetic fields originate, evolve, and eventually disappear as worlds cool below the threshold necessary for core convection. These lessons inform models of magnetic field evolution on Mars, Mercury, and the large asteroids that may have once possessed their own magnetospheres. The legacy of the lunar magnetic field persists in the form of magnetic anomalies that continue to influence surface processes billions of years after the dynamo ceased operation. These remnant fields create preferential sites for volatile accumulation, influence the trajectories of charged particles in the lunar environment, and preserve records of ancient magnetic field strength and direction that allow reconstruction of the Moon's thermal and rotational history through paleomagnetic analysis of returned samples. Only took the inexorable cooling of a small world to extinguish the magnetic field that once provided modest protection from solar wind bombardment. Only took the solidification of the lunar core to eliminate the convective motions necessary for magnetic field generation, exposing the Moon's surface to the full intensity of space weathering processes. Only took the loss of this invisible shield to transform the Moon into the magnetically quiet world that future space missions will discover, preserving in its ancient rocks the fading magnetic memories of a more geologically active youth when liquid iron still stirred in the lunar depths and cast protective magnetic loops into the vacuum of space. The most recent large impacts on the Moon's surface create brilliant ray systems that streak across the ancient landscape like cosmic artwork painted in bright pulverized rock. These spectacular features, invisible to the naked eye during most lunar phases but blazing with reflected sunlight during full moon, represent the freshest scars on the lunar surface, craters formed within the last few 100 million years when the bombardment rate had already declined to near modern levels. The rays extend for hundreds of kilometers from their parent craters, creating radial patterns of bright material that overlay the darker, more mature regolith with the geometric precision of explosion debris frozen in time. The formation of crater rays follows the same ballistic physics that governs all impact events, but their visibility depends on the optical contrast between fresh, unweathered rock and the space-weathered regolith that dominates most of the lunar surface. When a large meteoroid strikes the Moon at cosmic velocity, it excavates material from depths of several kilometers and hurls this subsurface rock across vast distances in all directions. The freshly exposed material retains its original brightness and spectral properties, creating high albedo streaks that stand out dramatically against the darkened background of mature lunar soil. Tycho crater, the most prominent rayed crater visible from Earth, formed approximately 108 million years ago when a kilometer-sized asteroid struck the southern lunar highlands with enough energy to excavate a crater 85 kilometers in diameter. The impact ejected billions of tons of pulverized anorthosite across thousands of square kilometers, creating ray deposits that extend more than 1,500 kilometers from the crater rim. These Tycho rays cross mountain ranges, traverse Mare plains, and overlay older craters with complete indifference to the pre-existing topography, demonstrating the enormous energies involved in large impact events. The physics of ray formation involves the complex interaction between high-velocity ejecta and the lunar gravitational field. Material launched from impact craters follows parabolic trajectories determined by their initial velocity vectors and the Moon's weak surface gravity. The fastest-moving debris travels the farthest, creating the longest rays, while slower ejecta falls closer to the source crater. The continuous spectrum of ejection velocities produces rays of all lengths, from short streaks extending only a few crater diameters to the longest rays that reach halfway around the Moon. The brightness of fresh crater rays results from the exposure of unweathered rock that has not yet experienced the space weathering processes that darken mature regolith over millions of years. Solar wind implantation, micrometeorite bombardment, and cosmic ray irradiation gradually alter the optical properties of surface materials, reducing their reflectance and creating the characteristic dark, neutral coloration of ancient lunar terrain. Fresh ejecta from recent impacts has not had time to develop these weathering effects, preserving the high reflectance and distinctive colors of the original bedrock. Copernicus crater, formed approximately 800 million years ago, displays a well-developed ray system that demonstrates the intermediate stages of ray evolution. The Copernican rays, though less brilliant than those of Tycho, remain clearly visible during favorable lighting conditions and extend several hundred kilometers from the 93-kilometer diameter crater. The reduced brightness of these older rays reflects the gradual darkening effects of space weathering operating over geological time, providing a natural laboratory for studying the rates and mechanisms of optical alteration on airless planetary surfaces. The composition of ray material reflects the chemistry of the target rocks excavated during crater formation, creating distinctive spectral signatures that allow remote identification of subsurface geology. Rays from highland craters consist primarily of anorthosite fragments with high aluminum content and bright, neutral coloration. Mare crater rays contain basaltic material with high iron and titanium concentrations that create darker rays with distinctive blue-gray spectral signatures. Mixed rays, formed by impacts that excavate both highland and mare materials, display intermediate compositions that record the local geological complexity. The temporal evolution of crater rays provides insights into the rates and mechanisms of space weathering on the lunar surface. Fresh rays, like those from Tycho crater, maintain high contrast with surrounding terrain for tens of millions of years before beginning to fade noticeably. Ancient ray systems, such as those associated with craters formed during the late heavy bombardment, have completely disappeared through space weathering, leaving no trace of their former brilliance. This optical evolution allows estimation of crater ages through ray visibility and provides calibration for space weathering models. The directional patterns of ray systems record the impact trajectories and velocities of the projectiles that created them. Symmetric ray patterns indicate nearly vertical impacts, while asymmetric patterns suggest oblique collisions that preferentially eject material in specific directions. The most energetic impacts create rays that extend in all directions with nearly equal intensity, while smaller impacts may produce rays only in the downrange direction where ejection velocities exceed escape velocity thresholds. Secondary crater chains associated with large ray systems demonstrate the complex cascade of impacts that follow major collision events. The largest ejecta blocks from primary impacts travel hundreds of kilometers before striking the surface and creating their own smaller craters aligned along the ray directions. These secondary impacts often occur in clusters or chains where multiple fragments from a single ejection event land in close proximity, creating characteristic patterns that distinguish secondary craters from primary impact features. The survival of visible ray systems requires specific combinations of impact energy, target material properties, and subsequent bombardment history. Small impacts lack the energy to excavate sufficient fresh material for visible ray formation, while the largest impacts may destroy their own ray systems through the intense heating and shock processing that accompanies basin-scale events. Intermediate-sized impacts, creating craters between 10 and 100 kilometers in diameter, provide optimal conditions for ray system development and preservation. The interaction between ray systems and local topography creates complex patterns of bright and dark terrain that vary with solar illumination angle and viewing geometry. Rays crossing elevated terrain appear brighter due to enhanced reflectance from steep slopes, while rays in low-lying areas may be partially obscured by shadows or contaminated by darker materials transported by mass-wasting processes. These topographic effects contribute to the time-variable appearance of ray systems as observed from Earth during different lunar phases. The chemical alteration of ray material occurs through multiple space-weathering processes operating on different timescales. Solar wind implantation darkens surface materials within thousands of years, while micrometeorite bombardment requires millions of years to significantly alter optical properties. Cosmic ray spallation operates over tens of millions of years to create distinctive isotopic signatures in ray materials. The combination of these processes creates the gradual fading of ray visibility that allows relative age dating of lunar impact features. The study of crater rays provides crucial information about the population and characteristics of impactors in the inner solar system during recent geological time. The size distribution of rayed craters reflects the size-frequency relationships of asteroids and comets that crossed lunar orbit during the last few 100 million years. Changes in ray crater formation rates over time record variations in bombardment intensity that may correlate with asteroid family breakup events or perturbations of comet orbits by giant planet migration. The mystery of ray asymmetries in some crater systems suggests complex interactions between impact processes and local geological conditions. Computer simulations indicate that subsurface structure variations, such as buried crater rims or density contrasts between different rock types, can influence ejecta distribution patterns and create preferential ray development in specific directions. These asymmetries provide insights into buried geological structures that are otherwise invisible from orbital observations. Only took the excavation of fresh bedrock by recent cosmic impacts to paint brilliant ray patterns across the ancient lunar landscape. Only took the contrast between bright, unweathered ejecta and dark, mature regolith to create the spectacular radial streaks visible during full moon from Earth. Only took the patient operation of space weathering processes, gradually darkening these fresh deposits over millions of years, to demonstrate the slow transformation of lunar surface materials and create the natural chronometer that allows measurement of geological time through the fading brightness of impact rays scattered like cosmic brushstrokes across the moon's eternally patient face. Even while locked in synchronous rotation with one face permanently turned toward Earth, the moon experiences subtle oscillations called librations that allow terrestrial observers to glimpse slightly beyond the geometric edges of the lunar disk. These gentle nodding and swaying motions, invisible to casual observation but measurable through careful telescopic study, result from the complex interplay between the moon's orbital characteristics and the gravitational forces that govern its motion through space, over periods of months and years. These librations reveal approximately 59% of the lunar surface to Earth-based observers, leaving only 41% permanently hidden on the far side. The physical origin of librations lies in the slight mismatch between the moon's uniform rotational motion and its variable orbital velocity as it follows an elliptical path around Earth. The moon rotates on its axis at a constant rate determined by the tidal locking that occurred billions of years ago, completing one rotation in exactly the same time required for one orbital revolution around Earth. However, the moon's orbital velocity varies systematically throughout each month according to Kepler's laws of planetary motion, moving faster when closer to Earth at perigee and slower when farther away at apogee. This variation in orbital speed creates longitudinal libration, an apparent east-west oscillation that allows observers to see approximately 8 degrees beyond each lunar limb over the course of a complete orbital cycle. When the moon moves faster than average in its orbit near perigee, its rotation cannot keep pace with the changing Earth-Moon line, causing the lunar surface to appear to lag behind and revealing regions normally hidden beyond the eastern limb. Conversely, when orbital motion slows near apogee, the rotation leads the orbital position, exposing areas beyond the western limb that are usually invisible from Earth. The elliptical shape of the moon's orbit, with an eccentricity of approximately 0.055, creates the primary driving force for longitudinal libration. This orbital ellipticity results from perturbations caused by the Sun's gravitational influence and the complex three-body dynamics of the Earth-Moon-Sun system. The variation in Earth-Moon distance throughout each month, ranging from about 356,000 kilometers at perigee to 407,000 kilometers at apogee, corresponds to changes in orbital velocity of several percent that translate directly into observable libration effects. Latitudinal libration, the apparent north-south nodding of the moon, arises from the 5-degree inclination of the lunar orbit relative to Earth's equatorial plane. This orbital tilt causes the moon to appear slightly north or south of the Earth-Moon line at different times during its orbit, allowing observers to peek over the north and south polar regions alternately. The amplitude of latitudinal libration reaches approximately 6.5 degrees, sufficient to reveal significant portions of both polar regions that would otherwise remain permanently hidden from Earth-based observation. The combination of longitudinal and latitudinal librations creates a complex pattern of lunar surface visibility that varies continuously throughout each month and over longer periods related to the precession of the lunar orbit. Certain regions near the limbs experience extreme libration effects, appearing and disappearing from Earth's view in cycles that can span months or years. These libration zones provide unique opportunities for studying the transition between the familiar near side and the mysterious far side of the moon. A third type of libration, called diurnal libration, results from the rotation of Earth itself and the changing perspective of observers at different terrestrial locations and times. As Earth rotates, observers move through slightly different viewing angles relative to the moon, creating apparent shifts in lunar position of up to 1 degree. This diurnal effect is most pronounced for observers near Earth's limb relative to the moon, where the perspective change due to Earth's rotation creates the maximum apparent displacement of lunar features. The mathematical description of librations requires consideration of the moon's complex rotational dynamics, including the effects of its slightly non-spherical shape and the gravitational torques exerted by both Earth and Sun. The moon's principal axis of inertia, aligned with the Earth-Moon line during synchronous rotation, experiences periodic torques that create small oscillations about the equilibrium position. These physical librations, as opposed to the purely geometrical effects of orbital characteristics, contribute additional complexity to the moon's apparent motion as viewed from Earth. The study of librations played a crucial role in the historical development of celestial mechanics and the understanding of gravitational interactions in multi-body systems. Early astronomers, including Giovanni Battista Riccioli and Johannes Hevelius in the 17th century, recognized that certain lunar features appeared and disappeared near the limbs with predictable regularity. This observation led to the realization that the moon's rotation and orbital motion were synchronized, providing evidence for tidal forces long before the physical mechanisms were fully understood. Modern laser ranging experiments that measure the Earth-Moon distance with millimeter precision have revealed additional subtle libration effects caused by the elastic deformation of both Earth and Moon under tidal forces. These tiny variations in the Moon's orientation, measurable only through the most precise techniques available, provide insights into the internal structure and composition of both bodies. The liquid water oceans on Earth and the solid but slightly flexible interior of the Moon respond differently to tidal stresses, creating distinctive signatures in the libration data. The libration zones near the lunar limbs contain some of the most challenging terrain for spacecraft exploration due to their extreme foreshortening as viewed from Earth and their periodic visibility changes that complicate navigation and communication. These regions often feature dramatic topographic relief where the curvature of the Moon brings mountain peaks and crater rims into stark silhouette against the lunar horizon. The lighting conditions in libration zones create spectacular scenery with deep shadows and brilliant highlights that reveal the three-dimensional structure of lunar topography. The South Pole Aitken Basin, the largest impact structure on the Moon, becomes partially visible during favorable libration conditions that allow observation of the southern limb regions. This ancient basin, stretching more than 2,500 kilometers across the lunar far side, represents one of the most significant geological features in the solar system. The libration visibility of its outer regions provides the only Earth-based views of this enormous impact structure and demonstrates the scientific value of systematic libration observations. The discovery of water ice deposits in permanently shadowed polar craters relies partly on libration effects that bring these regions into view during specific geometric configurations. The slight nodding motion of the Moon allows Earth-based radar and laser systems to probe crater interiors that would otherwise remain completely hidden from terrestrial observation. These libration-enabled observations contribute crucial data for understanding the distribution and characteristics of lunar polar volatiles. The prediction of libration effects requires sophisticated computer models that account for the gravitational influences of Sun, Earth, and Moon, as well as the subtle perturbations caused by other planets and the non-uniform mass distributions within Earth and Moon. These models achieve extraordinary precision, allowing calculation of lunar position and orientation centuries into the future with accuracy sufficient for planning spacecraft missions and predicting occultation events where the Moon passes in front of stars or planets as viewed from Earth. The cultural and historical significance of librations extends beyond their scientific importance to influence human perception and mythology surrounding the Moon. The gradual revelation of previously hidden lunar features during favorable libration periods creates an impression of lunar breathing or subtle animation that has inspired astronomical observers throughout history. This apparent vitality in an otherwise unchanging celestial body contributes to the Moon's enduring fascination and its role in human imagination and folklore. The mystery of anomalous libration behavior during certain lunar phases suggests that the Moon's internal structure may be more complex than simple models predict. Subtle variations in libration amplitude and timing that do not match theoretical predictions based on a uniform internal density distribution indicate the presence of mass concentrations or structural asymmetries within the lunar interior. These anomalies provide clues about the Moon's formation and early geological evolution that complement information obtained from seismic studies and gravitational field measurements. Only took the slight eccentricity of the lunar orbit and the 5-degree inclination of the orbital plane to create the gentle librations that reveal hidden regions beyond the Moon's apparent limb. Only took the mismatch between uniform rotation and variable orbital velocity to provide terrestrial observers with glimpses of the mysterious far side without requiring space travel. Only took the patient observation of these subtle nodding motions over centuries of study to reveal the complex gravitational dance that governs the Moon's motion and allows earthbound astronomers to map nearly 60% of the lunar surface from their home planet's surface, forever reaching toward the remaining hidden regions that await direct exploration. Deep within the moon's ancient and rigid interior, tidal forces continue to generate subtle but measurable seismic activity that reveals the internal structure and composition of our celestial companion. These moonquakes, detected by seismometers deployed during Apollo missions, differ fundamentally from terrestrial earthquakes in their origins, characteristics, and propagation through the lunar interior. The moon's solid, largely homogeneous structure allows seismic waves to travel vast distances with little attenuation, creating resonant vibrations that can persist for hours after the initial disturbance and provide unprecedented insights into planetary internal architecture. The primary source of lunar seismic activity derives from the tidal stresses imposed by Earth's gravitational field acting on the moon's slightly non-spherical mass distribution. As the moon follows its elliptical orbit, varying from 356,000 to 407,000 kilometers from Earth, the changing tidal forces create cyclic stress patterns within the lunar interior that occasionally exceed the strength of internal rock formations. These deep moonquakes, originating at depths between 700 and 1,200 kilometers below the surface, occur with remarkable regularity that correlates precisely with the moon's orbital position and the tidal stress cycle. The mechanism of tidal moonquake generation involves the gradual accumulation of stress within partially molten or highly fractured zones deep in the lunar mantle. As tidal forces vary throughout each orbital cycle, these weak zones experience alternating compression and extension that slowly builds toward failure thresholds. When the accumulated stress exceeds the material strength, sudden fracturing or slip occurs along pre-existing fault planes, releasing the stored energy as seismic waves that propagate throughout the lunar interior and eventually reach the surface where they can be detected by sensitive instruments. Unlike terrestrial earthquakes, which typically last only seconds to minutes, lunar seismic events can generate detectable vibrations for several hours due to the moon's highly efficient seismic wave transmission. The absence of water, atmospheric pressure, and significant internal heterogeneity means that lunar seismic waves experience minimal damping as they propagate through the solid interior. This creates a ringing effect where the entire moon continues to vibrate like a struck bell long after the initial seismic event, with waves reflecting and re-reflecting between the surface and core boundary multiple times. The Apollo Passive Seismic Experiment Network, consisting of 4 seismometers deployed between 1969 and 1972, operated continuously for 8 years and recorded more than 12,000 seismic events of various types and magnitudes. This dataset provides the most comprehensive record of seismic activity on any planetary body other than Earth and reveals the moon's internal structure through the analysis of seismic wave velocities, attenuation characteristics, and propagation patterns. The network's global coverage allows triangulation of seismic sources and detailed mapping of internal discontinuities and composition variations. Deep moonquakes exhibit a strong correlation with the moon's position in its elliptical orbit, occurring most frequently during perigee and apogee when tidal stress variations reach maximum values. The timing of these events, predictable to within days based on orbital mechanics, demonstrates the direct causal relationship between tidal forces and seismic activity. This correlation provides a natural laboratory for studying tidal stress effects on planetary interiors and offers insights into similar processes operating on other tidally heated bodies throughout the solar system. Shallow moonquakes, originating within the upper few hundred kilometers of the lunar crust and mantle, differ significantly from their deep counterparts in both origin and characteristics. These events appear to result from thermal stresses generated by the extreme temperature variations experienced during the lunar day-night cycle, which can exceed 250 degrees Celsius between maximum heating and minimum cooling. The expansion and contraction of surface and near-surface materials under these thermal cycles creates stress accumulation that occasionally results in brittle failure and seismic energy release. Meteorite impact events contribute a third category of lunar seismic sources, generating distinctive seismic signatures that differ markedly from tectonic moonquakes. Large meteorite impacts create instantaneous energy release that produces high-frequency seismic waves with rapid attenuation, contrasting sharply with the long period, long-duration signals characteristic of tidal moonquakes. The Apollo seismic network detected numerous impact events, including several large meteorite strikes that created new craters during the operational period of the seismometer array. The artificial seismic sources created by controlled impacts of spent Apollo spacecraft and lunar modules provided calibrated energy inputs for detailed studies of lunar internal structure. These deliberately crashed vehicles, impacting the surface at known times and locations with precisely calculated energies, generated seismic waves that traveled through well-defined paths to the seismometer stations. Analysis of these controlled source experiments reveals the existence of distinct velocity layers within the Moon, including a low-velocity zone at depths of several hundred kilometers that may indicate partially molten material. The seismic velocity structure, determined from moonquake analysis, indicates that the Moon possesses a layered internal architecture similar to terrestrial planets, but with important differences reflecting its unique formation and thermal history. The outer several hundred kilometers consist of relatively low-density crustal and upper mantle materials with seismic velocities characteristic of orthositic and basaltic rock compositions. Below this lies a higher velocity zone extending to depths of approximately 1,000 kilometers, composed primarily of olivine and pyroxene minerals typical of planetary mantle compositions. The discovery of a small liquid core at the Moon's center represents one of the most significant findings from lunar seismic studies. Seismic waves that would normally pass through the lunar center show distinctive patterns of reflection and refraction that indicate the presence of a liquid or partially liquid zone with a radius of approximately 330 kilometers. This liquid core, composed primarily of iron with smaller amounts of sulfur and other light elements, remains molten due to the concentration of radioactive elements and the insulating effect of the overlying solid mantle. The existence of the lunar liquid core helps explain several puzzling aspects of lunar evolution, including the ancient magnetic field generation and the complex rotational dynamics observed through precise laser ranging measurements. The liquid core provides a plausible mechanism for the magnetic dynamo that operated during the Moon's first billion years, while its current partially molten state contributes to the subtle variations in lunar rotation and orientation detected by modern observational techniques. Moonquake magnitudes, measured on scales adapted from terrestrial seismology, rarely exceed magnitude 5.5 and typically range between 1 and 4 on the Richter scale. These relatively modest energy releases reflect the Moon's lower internal stress levels compared to tectonically active planets like Earth, where plate motions and volcanic processes generate much larger seismic events. However, the efficient propagation of seismic energy through the lunar interior means that even small moonquakes can be detected at great distances from their sources. The temporal distribution of moonquakes reveals interesting patterns related to the Moon's complex orbital dynamics and tidal stress variations. Peak seismic activity occurs not only during maximum tidal stress periods, but also shows correlations with the Moon's position relative to the Earth-Sun line, suggesting that solar tidal forces contribute additional stress components that modulate lunar seismic activity. These multi-body gravitational effects create complex interference patterns in tidal stress that influence the timing and magnitude of seismic events. The frequency content of lunar seismic signals provides information about the source mechanisms and propagation paths that complement the timing and location data obtained from seismometer networks. Deep moonquakes generate predominantly low-frequency waves with periods of several seconds, consistent with large-scale brittle failure in strong rock under slowly varying stress conditions. Shallow moonquakes produce higher frequency content indicative of more rapid failure processes in weaker, more fractured near-surface materials. The study of moonquake source mechanisms reveals that most deep seismic events occur through shear failure along pre-existing fracture planes rather than through the creation of new fractures in intact rock. This indicates that the lunar interior contains extensive fracture networks, possibly inherited from the ancient bombardment period, when large impacts created shock fractures throughout the lunar interior. These inherited weakness zones focus stress concentrations and provide preferential failure surfaces for tidal moonquake generation. The geographical distribution of moonquake epicenters shows distinct clustering in specific regions of the lunar interior, suggesting that tidal stress concentration varies systematically with location due to the moon's non-uniform internal structure and mass distribution. The mascons associated with large impact basins create gravitational anomalies that influence stress patterns and may contribute to preferential moonquake occurrence in certain regions. This spatial clustering provides constraints on internal density variations and structural heterogeneities. The long-term monitoring of moonquake activity through the 8-year Apollo seismic experiment reveals systematic variations in seismic energy release that correlate with longer-period orbital cycles, including the 18.6-year precession of the lunar orbital plane and the 8.85-year rotation of the lunar perigee. These long-period modulations in seismic activity demonstrate the sensitivity of lunar internal processes to subtle variations in tidal stress, amplitude, and orientation, providing insights into the mechanical properties and failure criteria of materials deep within planetary interiors. The mystery of moonquake swarms, periods of enhanced seismic activity lasting weeks to months, suggests that lunar seismic processes may involve more complex stress accumulation and release mechanisms than simple tidal triggering. These swarm episodes, characterized by unusually high rates of moonquake occurrence, may result from stress redistribution following large seismic events or from changes in the mechanical properties of deep fracture zones due to fluid migration or thermal cycling effects. Modern reanalysis of Apollo seismic data using advanced signal processing techniques and improved understanding of seismic wave propagation continues to reveal new insights into lunar internal structure and dynamics. Computer modeling of seismic wave propagation through three-dimensional lunar interior models allows more precise determination of source locations and mechanisms, while sophisticated filtering techniques extract additional information from the complex, long-duration seismic signals characteristic of lunar events. The implications of lunar seismic studies extend beyond the moon itself to inform understanding of internal processes on other small planetary bodies throughout the solar system. The moon serves as an accessible natural laboratory for studying tidal heating effects, thermal stress phenomena, and the seismic properties of differentiated rocky bodies. These insights prove valuable for interpreting geophysical data from Mars, asteroids, and the moons of giant planets where direct seismic measurements are limited or unavailable. The future of lunar seismology points toward deployment of modern seismometer networks with improved sensitivity, broader frequency response, and global coverage that will extend and refine the pioneering measurements made during the Apollo era. These next-generation instruments will provide higher-resolution images of lunar internal structure, better characterization of the liquid core properties, and improved understanding of the ongoing tidal and thermal processes that continue to shape the moon's interior billions of years after its formation. Only took the patient accumulation of tidal stress within the moon's ancient interior to generate the subtle seismic activity that reveals its internal architecture to scientific study. Only took the deployment of sensitive instruments on the lunar surface to detect the faint vibrations of a world still responding to gravitational forces billions of years after its violent birth. Only took the analysis of thousands of moonquakes recorded over nearly a decade to discover that the moon remains a dynamically active body, its solid interior still yielding to the relentless tidal massage of its planetary companion and preserving in its seismic signatures the story of internal differentiation, cooling, and the gradual transition from molten chaos to the crystalline stability of cosmic deep time. The solar wind, a continuous stream of charged particles flowing outward from the sun at velocities exceeding 400 kilometers per second, sculpts the lunar surface through billions of years of atomic-scale bombardment that gradually transforms the mineralogy, chemistry, and optical properties of exposed rock. This invisible radiation, consisting primarily of hydrogen and helium nuclei accelerated by the sun's magnetic field and thermal energy, strikes the airless moon with undiminished intensity, embedding itself in crystal lattices and creating cumulative changes that operate on timescales spanning geological ages. Unlike the dramatic violence of meteorite impacts, solar wind alteration proceeds with molecular patience, modifying surface materials grain by grain through processes so subtle they remained undetected until the space age brought direct sampling of lunar materials. The mechanism of solar wind interaction with lunar minerals involves high-energy particle implantation that disrupts crystal structures and creates chemical reduction reactions at microscopic scales. When hydrogen nuclei strike silicate minerals at velocities of several hundred kilometers per second, they penetrate several tens of nanometers into the crystal lattice and create displacement cascades that knock atoms from their normal positions. This atomic-scale bombardment gradually amorphizes the outer surface layers of mineral grains, transforming crystalline structures into glass-like materials with altered optical and chemical properties. The most significant consequence of solar wind bombardment is the reduction of iron-bearing minerals through interaction with implanted hydrogen atoms. Lunar minerals containing ferrous iron, Fe2+, in their crystal structures undergo chemical reactions with solar wind hydrogen that produce nanoscopic metallic iron particles and water molecules. These nanoscale iron grains, invisible individually but collectively responsible for the moon's dark appearance, accumulate throughout the regolith over millions of years and create the distinctive spectral signature that distinguishes space-weathered lunar materials from fresh rock exposures. The production of metallic iron through solar wind reduction represents a fundamental alteration of lunar mineralogy that affects both the chemical and physical properties of surface materials. The nanoscopic iron particles, typically 10–100 nanometers in diameter, form within partially amorphized mineral grains and create continuous networks of metallic material that alter electrical conductivity, magnetic properties, and optical absorption characteristics. This space-weathered material exhibits enhanced microwave absorption and modified radar reflectance that can be detected by Earth-based radio telescopes. Solar wind helium implantation contributes additional chemical signatures to lunar regolith that provide records of solar activity and stellar evolution over billions of years. Helium atoms, too large to diffuse easily through crystal lattices once implanted, accumulate to concentrations of 10–20 parts per million in mature lunar soil. The isotopic composition of this trapped helium reflects the nuclear fusion processes operating in the sun's core and preserves a chemical archive of solar wind composition extending back through geological time. The rate of solar wind alteration varies significantly with the flux and energy distribution of the particle stream, which fluctuates on timescales ranging from minutes to millions of years in response to solar magnetic field variations and stellar evolutionary changes. During periods of high solar activity, enhanced particle fluxes accelerate space weathering processes, while solar minimum conditions allow slower, more uniform alteration rates. These variations create temporal layers within the regolith that record the Sun's magnetic and thermal history in the chemical signatures of implanted particles. The directionality of solar wind bombardment creates systematic variations in space, weathering intensity across the lunar surface that correlate with the geometry of particle exposure. Surfaces facing the average solar wind direction experience more intense weathering than those oriented parallel to the particle flow, creating subtle but measurable differences in optical properties that can be detected through careful spectroscopic analysis. These directional effects provide information about the long-term average orientation of the solar wind relative to the lunar surface. The interaction between solar wind and the Moon's tenuous exosphere creates complex plasma physics phenomena that influence both the particle bombardment rate and the escape of sputtered materials. When high-velocity solar wind protons strike lunar surface atoms, they transfer sufficient energy to eject sodium, potassium, and other elements into ballistic trajectories that create a thin cloud of neutral atoms surrounding the Moon. This sputtered exosphere, detectable through its emission lines when excited by solar ultraviolet radiation, represents a dynamic balance between solar wind input and gravitational escape. The accumulation of solar wind hydrogen in lunar regolith creates a substantial reservoir of potentially useful volatile material distributed throughout the upper layers of lunar soil. Concentrations ranging from 100 parts per million by weight represent millions of tons of hydrogen stored in the regolith across the lunar surface. This implanted hydrogen can potentially be extracted through heating processes and combined with oxygen from lunar minerals to produce water for future human exploration missions. The magnetic anomalies preserved in lunar crustal rocks from the Moon's early magnetic field period create localized variations in solar wind exposure that produce distinctive space weathering patterns. Regions with strong remnant magnetization deflect solar wind particles and experience reduced weathering rates, preserving more of their original optical properties than surrounding areas exposed to direct particle bombardment. These magnetic mini-magnetospheres create natural laboratories for studying space weathering processes under different exposure conditions. The chemical sputtering effects of solar wind bombardment gradually erode exposed surface materials and transport atoms across vast distances through ballistic trajectories determined by lunar gravity and electrostatic forces. The preferential sputtering of lighter elements creates compositional changes in the uppermost surface layers that differ from the bulk composition of underlying materials. This selective erosion process contributes to the formation of distinctive surface chemistry signatures that can be detected through remote sensing techniques. The temperature dependence of solar wind implantation and diffusion processes creates systematic variations in space weathering rates between lunar day and night conditions. During the 2-week lunar day, elevated surface temperatures enhance atomic diffusion rates and promote chemical reactions between implanted hydrogen and iron-bearing minerals. The extreme cold of lunar night slows these processes and allows different reaction pathways to operate, creating complex temporal variations in space weathering chemistry. The interaction between solar wind and impact-generated fresh surfaces creates rapid space weathering effects that can be observed on timescales of thousands of years rather than millions. Newly exposed bedrock from recent impacts lacks the protective coatings of space-weathered materials and experiences accelerated alteration under direct solar wind exposure. These rapidly weathering surfaces provide natural experiments for studying the initial stages of space weathering processes and calibrating alteration rate models. The study of solar wind effects on lunar materials provides crucial insights into space weathering processes operating throughout the solar system on airless planetary surfaces, asteroids, the moons of outer planets, and Mercury experience similar particle bombardment that creates analogous mineralogical and optical alterations. The Moon serves as an accessible laboratory for understanding these processes and developing techniques for interpreting remote sensing data from other space-weathered bodies. The discovery of water molecules produced by solar-wind mineral interactions represents one of the most significant recent findings in lunar science. Infrared spectroscopy reveals widespread hydroxyl (OH) and water (H2O) signatures across the lunar surface that correlate with solar wind exposure patterns and mineral compositions. This indigenous water production through space weathering processes supplements water ice deposits from comet impacts and provides additional resources for future lunar exploration. The long-term effects of solar wind bombardment contribute to the gradual darkening and spectral reddening that characterizes mature lunar regolith and distinguishes it from fresh rock exposures or meteorite samples. This optical evolution proceeds continuously over millions of years and creates the characteristic appearance of ancient lunar surfaces observed through telescopic and spacecraft imaging. The rate of this optical maturation provides a relative age dating technique for lunar surface features. The mystery of compositional variations in space weathering, effects between different lunar regions, suggests that local factors such as mineral composition, grain size distribution, and thermal environment influence the efficiency and products of solar wind alteration processes. Highland regions dominated by anorthositic minerals exhibit different weathering signatures than mare areas rich in basaltic materials, creating distinctive spectral characteristics that can be mapped through the orbital remote sensing. Only took 4 billion years of continuous solar wind bombardment to gradually transform the crystal-clear minerals of fresh, lunar rock into the dark, glassy materials that coat every exposed surface. Only took the patient implantation of hydrogen and helium nuclei, one atom at a time, to create the nanoscopic iron particles that darken the Moon and preserve chemical records of solar evolution in the regolith archive. Only took the inexorable operation of atomic-scale weathering processes to sculpt the lunar surface with molecular precision, creating the mature, space-weathered appearance that characterizes our celestial companion and demonstrates how even the gentlest cosmic forces can transform entire worlds when given the vast spans of astronomical time. The Moon continues its eternal watch over Earth, unchanged in human memory, yet constantly evolving on geological timescales through processes so gradual they remain invisible to casual observation. 4.5 billion years after its violent birth from the collision of worlds, the lunar companion maintains its patient vigil with the same face perpetually turned toward our planet. Its surface scarred by the accumulated impacts of cosmic ages, yet stable enough to preserve the footprints of visitors for millions of years in the windless silence of space. The forces that shaped the Moon in its youth, tidal friction, bombardment, volcanism, and magnetic field generation, have largely ceased their dramatic work, leaving behind a world where change occurs on timescales measured in geological epochs rather than human generations. The modern Moon experiences impact events at rates far reduced from the intense bombardment of its early history. Yet, meteoroids continue to strike its surface daily, adding microscopic contributions to the regolith layer and occasionally creating small craters detectable by high-resolution orbital cameras. These contemporary impacts, ranging from cosmic dust grains that vaporize on contact to rare meter-sized objects that excavate fresh craters, maintain the slow process of regolith gardening that mixes and homogenizes the lunar soil. Each impact, regardless of size, represents a continuation of the same processes that created the heavily cratered highlands and excavated the basins that later filled with basaltic lava to form the Maria. The temperature extremes experienced at the lunar surface continue to cycle between the searing heat of 2-week days and the frigid cold of equally long nights, driving thermal expansion and contraction that gradually weakens rock structures and contributes to the slow mechanical breakdown of exposed materials. These temperature variations, ranging from 120 degrees Celsius in direct sunlight to minus 170 degrees Celsius in permanent shadow, create stress patterns within rocks and regolith that accumulate over thousands of thermal cycles to produce fracturing and grain-scale fragmentation. Solar wind bombardment persists at its patient atomic pace, continuing to implant hydrogen and helium nuclei into surface minerals and gradually altering their chemical and optical properties through space weathering processes that operate on million-year timescales. The nanoscopic metallic ion particles produced by these interactions continue to accumulate throughout the regolith, slowly darkening the lunar surface and creating the mature spectral signature that distinguishes ancient terrain from fresh impact exposures. This ongoing space weathering represents the primary surface modification process active on the contemporary Moon. The Moon's orbital evolution continues through the same tidal friction mechanisms that have operated since its formation, gradually transferring angular momentum from Earth's rotation to lunar orbital motion and increasing the Earth-Moon distance by approximately 3.8 centimeters per year. This rate, measured precisely through laser ranging to retroreflectors placed on the lunar surface by Apollo missions, represents a continuation of the process that began when the Moon orbited much closer to Earth and exerted far stronger tidal forces on our planet's ancient magma oceans. Deep within the lunar interior, the small liquid core continues to cool slowly while maintaining partial convection that may occasionally generate weak magnetic fields detectable by sensitive magnetometers on orbiting spacecraft. The gradual solidification of this core represents the final phase of the Moon's thermal evolution, concluding a cooling process that began with the crystallization of the global magma ocean billions of years ago. When complete solidification eventually occurs, the Moon will lose its last internal source of geological activity and achieve complete thermal equilibrium with space. The regolith layer continues to thicken at imperceptible rates as micrometeorite bombardment pulverizes exposed bedrock and adds fine-grained material to the soil column. This process, operating continuously since the formation of the first solid crust, has created soil depths ranging from several meters in young mare regions to 15 meters or more in ancient highland areas. The thickness variations provide natural chronometers that record the exposure age of different geological units and demonstrate the relationship between bombardment history and surface evolution. Moonquakes generated by tidal stress continue to occur with predictable regularity as the Moon's orbit carries it through the elliptical path that creates varying gravitational forces within the lunar interior. These deep seismic events, clustering around perigee and apogee when tidal stress reaches maximum values, represent the primary manifestation of ongoing geological activity on the otherwise quiescent Moon. The seismic energy released by these events remains small compared to terrestrial earthquakes, but their occurrence demonstrates that the Moon retains mechanical responses to external forcing even billions of years after its formation. The polar regions of the Moon continue to accumulate volatile compounds in permanently shadowed craters where temperatures remain below the sublimation point of water ice throughout the lunar day-night cycle. These cold traps preserve not only water ice delivered by comet impacts throughout lunar history, but also other volatile species, including carbon dioxide, ammonia, and organic compounds that provide chemical archives of early solar system conditions. The gradual accumulation of these materials represents one of the few ongoing depositional processes active on the modern lunar surface. The Moon's role as Earth's stabilizing companion continues to moderate our planet's axial tilt and prevent the chaotic climate variations that would occur without lunar gravitational influence. This stabilizing effect operates through the same tidal torques that maintain the Moon's synchronous rotation, ensuring that Earth's obliquity remains within narrow bounds, favorable for stable climate patterns and the maintenance of conditions suitable for complex life. The gradual weakening of these stabilizing forces as the moon recedes will eventually allow greater climate instability, but not for hundreds of millions of years. The far side of the moon remains one of the most pristine environments in the inner solar system, shielded from terrestrial radio interference and largely protected from the particle bombardment associated with Earth's magnetosphere. This hemisphere preserves conditions representative of the early solar system and serves as a natural laboratory for studying processes that shaped planetary surfaces throughout the cosmos. The regolith on the far side contains more complete records of ancient solar wind composition and cosmic ray bombardment than materials from the Earth-facing hemisphere. The mystery of ongoing lunar shrinkage, detected through analysis of high-resolution imagery that reveals recent fault scarps and wrinkle ridges, suggests that the moon's interior continues to contract as residual heat slowly radiates away. These young tectonic features, estimated to be less than 1 billion years old, indicate that the moon remains mechanically active despite its apparently static appearance. The global pattern of these features provides insights into internal stress distributions and the response of lunar materials to ongoing thermal evolution. Libration effects continue to provide terrestrial observers with varying views of approximately 59% of the lunar surface as the moon's apparent orientation oscillates due to its elliptical orbit and axial tilt. These gentle nodding motions, imperceptible to casual observation but measurable through careful study, represent ongoing dynamical effects of the complex gravitational interactions that govern the Earth-Moon system. The precision measurement of these librations through laser ranging provides insights into the moon's internal mass distribution and rotational dynamics. The moon's exosphere, maintained by solar wind, sputtering, and impact vaporization, continues to cycle atoms of sodium, potassium, and other elements through ballistic trajectories that create a tenuous atmosphere with surface densities less than 1/trillionth that of Earth's atmosphere. This dynamic system responds to variations in solar activity and meteoroid bombardment rates, creating subtle changes in atmospheric density that can be monitored through spectroscopic observations of emission lines produced when exospheric atoms interact with solar ultraviolet radiation. Future evolution of the moon points toward continued gradual cooling, orbital recession, and the slow approach toward tidal equilibrium with Earth when both bodies will maintain the same face toward each other in a double-locked configuration. This distant future state, estimated to occur tens of billions of years in the future, represents the final stable configuration of the Earth-Moon system and the conclusion of the orbital evolution that began with the formation of both worlds. Long before this equilibrium is achieved, however, the Sun will have evolved beyond its current main sequence phase and altered the conditions throughout the inner solar system. The Moon's legacy as Earth's companion extends far beyond its gravitational and tidal influences to encompass its role in inspiring human curiosity about the cosmos and serving as humanity's first destination beyond Earth. The lunar surface preserves the landing sites of robotic and human missions as permanent monuments to the species that first achieved spaceflight and ventured beyond their home planet. These sites, protected by the vacuum preservation of the lunar environment, will remain unchanged for geological timescales as testimony to human exploration. Only took 4 billion years of patient cosmic evolution to transform the molten sphere born from planetary collision into the familiar silver companion that illuminates Earth's nights and stabilizes its climate. Only took the gradual operation of cooling, bombardment, and tidal forces to create the geological museum that preserves early solar system history in its craters. Maria and Highland Rocks. Only took the inexorable passage of time to establish the eternal watch that continues today, as the moon maintains its silent vigil over Earth with the same face that witnessed the rise of life, the evolution of consciousness, and the first tentative steps of a curious species toward the stars. forever patient in its cosmic dance through the darkness of space. The moon drifts silently through the star-filled darkness above, its ancient face serene with the patience of geological time. 4.5 billion years of cosmic history rest in the gentle silver light that bathes the night landscape below, carrying within each reflected photon the memory of violence transformed into eternal peace. The craters sleep in their circular perfection. The Maria lie still as mirrors of polished stone. The highlands glow with the soft radiance of anorthosite that crystallized when the solar system was young and worlds were still forming from cosmic debris. In the vacuum of space around the moon, individual atoms drift on ballistic trajectories, following Newton's laws with mathematical precision through the invisible exosphere. Sodium atoms rise from the regolith in graceful parabolas. Helium nuclei from the solar wind embed themselves in crystal lattices with atomic gentleness. Cosmic dust settles grain by grain onto surfaces that will preserve each microscopic impact for millions of years in the windless silence. The liquid core stirs slowly in the lunar depths, its molten iron cooling toward the final solidification that will mark the end of internal geological activity. Tidal forces flex the ancient interior with rhythms measured in months and years, creating deep moonquakes that ring through solid rock like whispers of gravitational memory. The moon remembers its formation in the language of seismic waves and magnetic field remnants frozen in highland stones. Far below, Earth turns beneath clouds and weather, its surface constantly renewed by wind and water and the patient work of living systems. But above, the moon keeps its eternal watch unchanged, one hemisphere forever gazing downward while the other dreams in permanent darkness. The far side preserves its secrets in impact scars and chemical signatures that tell stories of bombardment and differentiation written in stone and regolith over cosmic ages. Time moves differently in the lunar realm, where moments stretch into geological epochs and the only sounds are the silence of vacuum and the whisper of solar wind against naked rock. Here, change occurs on scales beyond human comprehension, measured not in heartbeats or seasons, but in the slow accumulation of space weathering and the patient gardening of micrometeorite impacts. Each crater tells its story to the cosmic dark. Each ray system blazes with the brightness of fresh rock excavated by recent violence. The moon's gravity reaches across the 250,000 miles to Earth below, raising tides in ocean and molten core with the same mathematical precision that once lifted mountains of liquid rock in the ancient magma seas. This invisible connection binds the two worlds in their eternal dance, exchanging angular momentum through tidal friction and slowly pushing them apart as the cosmic clockwork unwinds toward distant equilibrium. In the deep silence of lunar time, consciousness seems an impossibly brief flicker against the vast patience of stone and vacuum and electromagnetic radiation flowing through empty space. Yet this same cosmic quiet that watched the emergence of life from primordial seas and the first tentative steps of awareness toward understanding will continue its vigil long after the last observers have returned to stardust. The moon's silence encompasses all sound. Its darkness illuminates all light. Its stillness dances with the patient motion of worlds through space and time. Sleep comes gently to those who rest beneath the moon's ancient light, carried into dreams by the same gravitational forces that shaped both worlds from cosmic collision. The silver radiance that touches sleeping faces carries within it the distilled essence of 4 billion years of cosmic patience, the accumulated quietude of a world that has learned to wait with the composure of stone and the serenity of vacuum and the eternal stillness of time itself.